Morning. So we are ready to start the scientific section of this morning. We will have 5 talks, 3 before the coffee break and 2 after coffee break. And the first communication will be delivered by our friend, Professor Jürgen Stilk.
Alô? Isso aqui posso pôr aqui, sei lá.
Segura aquele.
Ah, tá. Ah, ok.
No princípio, esse aqui passa para frente, esse passa para frente.
Ah, ok. Como é que passa para trás?
Esse de baixo, de baixo.
É, ele está passando para frente. Como é que passa para trás? É. E pra...
Esse é o de baixo.
Ah, o de baixo, tá.
De baixo e de cima para frente.
Ah, ok. Okay. Good morning. It's a pleasure to see you all here. Many friends, long time. Unfortunately, I'm not able to be here all the days as I would like to. But anyway, it's very nice to be here today and to talk to you about something. Some of you already saw part of this in our autumn meeting some time ago. It's a work with Pablo Serra from Cordoba, Argentina, my friend Wellington from my university, Universidade Federal Fluminense, and myself. And well, it's trimers on a square lattice. It's a work using transfer matrices, so we will see. And well, I will start. It's a special meeting today. It's not our regular annual meeting. We have a very special friend today. I will talk a little bit about Constantino and myself, how we met and all this, I think. And then there will be a brief introduction, and then we'll say how we do these calculations, some results. It's a work in progress. I hope someday we will end it. I don't know, but probably by the end of this year. Pablo will be here in December, and so we're thinking about concluding it next month. Okay, I always, it's the same with Murilinho. No, yesterday I was not here, unfortunately, but you talked about Murilinho and some time ago. When I met Murilinho the first time, and so it's the same with Constantino. And it was, I think, I may be wrong, in the same year, 1978, I met Constantino. And there are 2 possibilities. I didn't go to the internet to find out. It's not relevant. Cambuquira was first? Not Recife. No, 78 was the first Cambuquira. And this workshop with Michael Fisher. This was in the same year. This was in Recife. Maybe one was in March, the other in June. I don't know. I didn't go up, you know. Ah, I put Caxambu. Ah, yes. So, well, I'm 70, okay? So please, yeah. Ah, now I understood. Yes, you were there. Many people with white hair were there, okay? It was the first meeting. It was the first meeting of the Brazilians in condensed matter physics, you know? I was just at the end of my master's degree. Salinas was one of the organizers. Probably that's why I was there, because, you know. Okay. Constantino was in both meetings, and I wanted to show you a photograph of the second thing, you know, because I don't have a photograph of the first with Constantino. I know many things of the first one. For instance, Constantino trying to get Salinas, my supervisor, to dance a tango in some place there, you know, at night. He didn't succeed, yes. No, Constantino, not with Constantino, of course. With some of the very few women who were around. Of course, there were many, many men, as usual, you know. At this time, very, very few women. Constantino tried. I think he wanted to Tsallis to dance something, and Tsallis said, I only know how to dance tango. So somebody found a record with tango at this place, you know. And, but even so, you were not successful, right? It didn't work out. But anyway, so last year, I knew with this workshop with Michael Fisher in Recife that Sergio Rezende took some photographs. So I asked him, and he sent me this photograph. So I would like to show it. It's not good, you know, but this is this photograph of this workshop. You see, there are many people here. Well, of course, Michael Fisher here, you see, and here in the back, it's very difficult to see, but here's Constantino, you see, here's Constantino. Mauricio Coutinho is here, you see, Brady here, Fittipaldi in the back here, you see, some people, right? One woman, I don't know who she is, sorry, but the photograph is not good. This is 78. I don't know why this 2004. Belita, maybe Belita. Yeah, maybe Belita, yes. And then you see here Carlos Mauricio Chaves, right, from PUC, I think that's him. And here you see, here this little part of a face is Salinas, you know, that's me. I always appear in these photographs for some strange reason. I'm always there. Fittipaldi is here, you see, here's Fittipaldi, here's Constantino, of course. And here, almost hidden, is my good friend from high school. He was my friend at high school, Carlos Okoye, who also left us too early. See here, Carlos Okoye, behind this guy, who I don't, okay? It's a very nice photograph. It was a very nice meeting, you remember, in Recife, right? Okay, I already, was too long already, so so Constantino, thanks a lot, many, many years. I learned a lot with you, and you in particular, all friends here from this institute, supported me very much all these years. So thanks. It's an opportunity to thank you for all this support I received from you and friendship, which is the most important thing, of course. Okay, so let's go down to business. You know, one of the few exact solutions on two-dimensional lattice, a long time in the 60s, is the problem of the entropy of dimers. You put dimers on the square lattice and ask how many configurations are there. Just excluded volume, athermal, no temperature, no energy, okay? And again, we just saw him in the photograph, okay? That's Castelline. At the same time, one of these problems, in physics, it's like this. Sometimes problems are ripe, and suddenly different people independently get the same result. And that's one of these examples, you know. Castelline, and then Temple and Fisher, all 61, okay? The entropy of dimers on the lattice, okay? Then you can think, okay, now what if we generalize this problem? Consider trimers, tetramers, you know, you have rods, straight rods on the square lattice. You can generalize this to other two-dimensional lattice, but huh? Yes, that's my PhD student. He doesn't look quite like you, but anyway, maybe he is a grandson. I don't know. Okay, so let's call them K-mers, you know. K can be 2 for dimers, 3 for trimers, 4 for tetramers, and so that's, you know, the generalization. Of course, then you don't have exact solutions, right? And also in the full lattice limit, okay? Of course, you can think of this in other limits, but Deepak Dar and Rajesh, who are my collaborators also, they did a lot on this, but I don't have time to this. And we looked at this in the full lattice limit some time ago, and I already talked about this here. And here you have these results, you see? Well, using transfer metrics, the same thing I will talk later on. Here you have the results for using transfer metrics. These are estimates. Of course, there is an exact result for k equals 2, that's dimers. See? we get this result with this limit, enter here for trimers, tetramers, and so up to k equals 10. Okay, and some time ago, people from Argentina and Chile did the same estimates using simulations. Okay, Pazinetti, Ramirez, Pastor, and so on. Okay, and it's nice because after many other situations where I don't do much simulations, and always they are in front of me, you know. So this is one of these few situations where I get better results than simulations. Oh, really? Oh, nice to meet you. Oh, well, that's really nice. So, okay. Yeah. So, yeah, nice to meet you. I know Ramirez Pastor, but I didn't know you. So it's nice to see you here. Okay. So you did a simulation some time ago in this problem, and you probably saw this. Yes, yes, I know you are working on, and I'm following your work. It's very nice work. Yes, we can talk after this. Oh, you see, the word is smaller than you suppose. Yeah, that's their results. Okay. Okay, but what I will talk, that's results. We now think about trimers, but we say, oh, they have not to be straight. They can be bended. Okay, just two edges, 3 monomers. They can have 2 configurations, either straight, weight 1, or bended, weight omega. Okay, so that's the problem I will talk to you. Okay. Again, full lattice limit. So they have to cover the whole lattice. I'm looking at this limit. And I'm using, again, as in this problem I talked about transfer matrices. What we do is solve the problem on stripes. I see strips here, but it's stripes of finite width, L. Okay, and solve it exactly on larger and larger widths, and then extrapolate it to the 2-dimensional limit. That's the usual techniques. The case of straight trimers or rods was studied before by Ghosh, and also, of course, in this paper, our paper from this year, which I already taught you about. And Ghosh and Deepak Dar again and Jacobson some time ago, and again by us before in this more general problem. And also the case where all the trimers are bended, I mean, forming a right angle, was also studied before in the literature by these people from Germany, Bonnemeyer, Jekyll, and Froboese, okay, 96. With similar techniques, also with transfer matrices. All those 2 papers are also with transfer matrices. Okay, here you see what I mean. You have a strip with width 4. Okay, why this? Here. Okay, 4. And you have some bended trimers, straight trimers. You have periodic boundary conditions, you see. Okay, and here I'm already giving a hint how we built the transfer matrix. What you have here, you have this dashed lines. Okay, and these are the states of the matrix. For instance, this state is 0, 0, 0, 0. This state is 0, 1, because I have 1 monomer incorporated here, 0, 0, 0, 1, 0, 1, and so on. 0, 0, 1, 2. Here I have 2 monomers, and that's how you build the matrix. So we don't have to go into details, okay? But that's the states of the matrix. That's a conventional way. I will say another one later. So that's the conventional way to build a matrix, is to include L sides of the lattice each time you apply the matrix, okay? And defining the states by the configurations of the L vertical edges cut by the horizontal line. For instance, here, the starting states is 0, 0, 0, because there's no edge of trimer here. But here you have the state 0, 2, 1. Here you have again the state 0, 0, 0. And here you have the state 1, 1, 1. These are, I mean, output states of this initial state. And so it goes, okay? And if you think about, if you start with this state 0, 0, 0, and you think a little bit, you will see that this matrix here, in this case, with 3, is a 4 by 4 transfer matrix, okay? So it's a size 4, 4 by 4, if with 3. And then, of course, you want to extrapolate to the two-dimensional limit, which is L going to infinity. So your task is to go to larger and larger stripes. Okay? That's this case. And if you go now to larger stripes, please go ahead. Oh, you don't want to? Okay. The size of the transfer matrix, as usual, grows exponentially with the size of the stripe. And he's kind of strikes here. He doesn't want to. See, here's the size. 3, you have 4 by 4 matrix, and we went up to 19. That's the size of the matrix with 19. Of course, you use symmetries, reflection symmetry, rotation symmetry. That's already the size of the matrix with symmetries, as it was in this case 3. Okay? You try to. And then, usually, as you know, really pointing, no. In the thermodynamic limit, as you know, the free energy per lattice site will be related to the leading eigenvalue of this transfer matrix. Okay, so that's the expression. And then use thermodynamics. Not too far, not too close. Okay, use thermodynamics and you get the entropy there. All this, it's a little tricky because, of course, this derivative has to be done numerically. Okay, but you have to be. Anyway. What's an alternative way? This I didn't talk about in the meeting. And we do this two ways, is to define the state not by this cut of the stripe, but the profiles of the upper end of the stripe. When you fill up the stripe with trimers, at some place you have a profile, which is already full and the rest is empty. This is a different way to define the transfer matrix. Why we did this? Because with this alternative way, the transfer matrix is smaller, which is of course good. Okay? What you do is to add, in this case, a variable number of trimers. So in a way, you have to put this into quotes. It's a kind of a grand canonical way to do things, because you don't add, for instance, in this case, in the conventional way, you add 3 monomers at each step of the transfer matrix. Here, you add a variable number of trimers each time you apply the transfer matrix, and enough to cover the lowest level of the profile. If you have a profile, there is something as a valley, which is the lowest level, and you cover this valley. That's the rule. I will show some drawings, you will see. And in this case, since you put a variable number of trimers, you have to put a variable as the activity, Z, okay? In this case now, a straight trimer, of course, has a weight Z, and a banded trimer has a weight omega times Z. Okay? This worked very nicely at the beginning, but ok. Não sei se tá muito lento. Eu estou usando, mas ele custa muito a... Bom. Ok. Don't worry. I think it's just... Esse também tá lento, tá vendo? Agora sim. Here are possible outputs of the profile. 2, 1, 0. That's the original profile. I have to cover this valley, which is 0, the level 0. Okay? And I could put a banded trimer here, you see? I cover this. Or I could put the straight trimer here. If I put the banded trimer, I get the profile 0, 0, 0. If I with weight WZ. And if I put a straight trimer on this valley, weight Z, I get the profile 1, 0, 2, which, by the way, using the symmetry, is exactly the same state as I had at the beginning here, right? So that's how it works. I get the profile, and then I see what the output is, and I build the matrix, okay? Now you see, in this formulation, the volume occupied by the stripe, if you apply the matrix m times, is variable for different sequences of the states. Let me give you a simple example. I don't have time to get into the details. But let's say it depends on the sequence of states you go through. Imagine you have, again, the width 3, as I put in the drawing before. And imagine that at each time, I put the horizontal trimer. I begin with 0, 0, 0, and put the horizontal trimer. If I apply m times the matrix, the size of my column is just 3 times m. No? Because the number, the volume I say is the number of sites. Okay, it's 3 times m. But I could apply at each time I apply the matrix 3 vertical trimers. You see? Then it would have size 9 times m. So the volume is variable. So this took us a long time to realize how to get rid of this z. Okay, the activity. So what you have actually, and that's what I say here, is in this problem, is that you don't have you have to have a strip which is larger than the largest possible sequence of timers you have. So what you have there is actually a coexistence of a phase in the bottom of the strip where you have the timers, a dense phase, and on the top you have vacuum. So you have a phase coexistence. Coexistence of the trimers in the bottom and vacuum in top. And when you have phase coexistence, what is necessary? You have to have the same free energies of the two phases. Well, the free energy of the vacuum is 0. Okay, so this is the way to get rid of the z. Okay, and the free energy of the the free energy of the dense phase is this one, of course, the leading eigenvalue and all this. And the free energy of the vacuum is 0. And this will determine the activity. Okay? So I'm getting close to the end because the results are few. And then from this you can get the entropy. It will depend on z. But this is the entropy per monomer already. The number of where did you see? Yeah, there's a minus sign missing. You're right. Okay, but it's okay, the expression. You're right. The entropy has to be, there is a minus sign, of course. That's thermodynamics. Okay. The number, that's the mean number of rods, of course, you get already from the free energy also. It appears there. And Z is determined by the coexistence conditions I taught you before. Okay? So that's how this works. But, you know, numerically it's harder because you have to solve also numerical these conditions. So it gets you more work. The transfer matrix is smaller, but you have to have more work you have not only to calculate this derivative numerically here, but you also have to get the value of Z solving numerically this equation. Okay. So finally, I think I get to the results as soon as I switch the slides. And try different possibilities. Well, okay, here's the transfer matrix for the case equals 3. You have some examples here. Okay, well, I will go faster here. I don't know how the time is going. Sorry, I didn't. 3 minutes. Yeah, I'm getting close. You see, you start with 0, 0, 0. Then you have these two possibilities: 3 vertical trimers, 1 horizontal, and then you have this. And in this case, you see, that's all the possible outputs of the initial horizontal state. And there are two, the same state and the other one. And actually, in this case, you remember in the other case, the matrix was 4 by 4, and you have a 2 by 2 matrix. So that's the advantage of this method. It's a smaller matrix. And this is a general rule, you know. And so the profile methods leads, as I already said to you, to smaller transfer matrices. But Murphy's law, As L grows, you know, the sizes get closer to each other. I mean, the quotient of the two sizes gets closer to 1, unfortunately. To estimate the entropy, you know, the entropies of the rods, they have different finite size behavior depending of the ratio of L to 3, okay? This air. So you have air is the remainder of L divided by 3. So you don't have an uniform sequences, but actually you have 3 sequences, okay? So the extrapolation procedure is a little bit tricky. In general, it depends of K. For instance, if you look at tetramers, you have 4 sequences to extrapolate and stuff. So we use this Bullish-Stir algorithm. The leading, behavior is 1 over L squared. And here are some results, you know. We use this variable omega, capital omega, you know, because omega 0 is straight rods and capital omega equals to 1 is the limit of all rods in a right angle, okay? And here are some of our results. These are still results all with the conventional methods. We are still working with the profile methods right now. And I think that's the last slide. There's some conclusions. Part of this is already published this year, you see. And here you have a picture of capital omega. So this is the straight rods, the result we had before, you know. You have a maximum at capital omega equals 1/2, which correspond to omega equal 1, where the two configurations have the same weights. And here, at this limit, capital omega equals 1, you have the limit of all rods at a right angle. And there are some behaviors, you know, we looked at what's the behavior in this region, what's the behavior in this region. We adjusted some curves here, you know. And just to finish, we are now generating more precise estimates for the entropy. So they're not very precise right now, but we are using larger matrices. And so the idea is to have good estimates for the finite size amplitudes A over L2, because there is, you can estimate the central charge and so, as Deepak Dar and his collaborators did for the problem of straight rods. So we are aiming at this in this direction. But for this, you have to have better estimates. For the graph, it's okay. You know, you have 4 or 5 digits. But to estimate the amplitude of the correction term, you have to have more precise estimates. And this requires more numerical work. Thanks a lot.
Thank you, Jürgen. So we have time for questions.
Yes. Ah, yeah, this one is there too. You're right. Yes, yes, yes. Sorry, it was not complete. It was 2 examples, but I was lazy. It's another example. That's well. Yeah, that's another. It's not complete. Yeah, you're right, but it doesn't lead to a new state. That's right.
So thanks for this talk. It's becoming clearer to me since the
Ouro Preto. I always say Caxambu, Cambuquira.
It's generic. But is there in this space of chemical potential and omega, is there really a phase transition for trimers on the square liners?
You mean in the non-dense limit?
Yeah, either way, either in the fully, well, then of course you don't have chemical potential. But in any case, does this system exhibit a phase transition?
I don't think so.
So what does it mean to talk about phase coexistence?
Well, you know, Well, let me talk few words about this. We devised this, and then we had this activity Z. How to get rid of this Z? Okay, what you do there is that you force phase coexistence because of the way you build things. You know, you put all the trimers at the bottom of a strip, and also, I mean, in order, okay, if you have in the grand canonical ensemble, you have the volume. When I first did the transparency, I put the volume there, but then I said, oh, they will ask me about the volume, so better don't put the volume. Okay, but there should be a volume or the number of sides of your lattice, let's say. Okay, but in order for things to work, the volume has to be big enough for, if you apply the matrix m times, as I said, you know, to accommodate all the trimers. And the number is variable depending of, you know, how you put things in there. That's the problem. So you have to put the volume big enough. So in any realization, you have at the bottom, you have phase coexistence, not because there is a phase transition, because you have no interactions between the timers, but you force them to be so. Okay, it's a little bit tricky, but by construction, you have a dense phase coexisting with the vacuum. Not because the system is so, but you don't allow for vacancies inside the trimers. Right? You force by construction the phase to be dense. Okay, it is as if well, it is, you are in the condensed phase, not because the interactions has driven the system into this phase, but by construction. And well, I should say pragmatically, when I first saw this. Since we're friends, I can, if Michael Fisher were here, so I would not say this. But when I first saw this, oh, you have an entropy. You have a variable there. You want to get rid of it. What would you do if you don't know what to do? You maximize the entropy. And I did this, and it worked. Because I knew the result by the conventional method, you know? And it worked, right? That was what I did. But then I said, well, if I have to justify what I did here, no way. So I have this other argument, but it's still strange. I agree with you, but at least it has some physical reason. I have a dense phase at the bottom of the thing. Physically, I mean, usually in the grand, so that's why I said grand canonical between quotes, because they don't have an attractive interaction between them. Why should they be all on the bottom of the stripe? But they are there by the construction. On the other side, you have the vacuum at top, with free energy 0. So they are coexistent. And again, it leads to the same result I had before, just maximizing the entropy for no reason at all. So that's more or less the real story behind of this. But we had a long time to realize how, you know? And this idea was based on some construction by Deepak Dar and Rajesh, who did a generating function argument to get a lower bound to these entropies. Okay, we adapted this to a transfer matrix.
A small question. Do you expect the central charge to be a number between 0 and 1 for this model?
I'm not sure, Constantino. I have to look and tell you afterward, because actually, Gosh, Dar, and Jacobson did this. The problem is I'd like to talk to Dar about this. We don't did it yet because I don't understand it really good. First of all, as I told you, the finite size scaling behavior depends on the ratio of the width to 3. So for trimers, you have 3 different amplitudes. So I have 3 different central charges. You know? Now, we expect probably this to depend on omega. So I have to talk to somebody like Chico Caras or even Deepak Dar to understand first, what does this mean? You see, you have a multitude of values. So what does this mean, really? You know, we are still starting with this because we still don't have enough precision. But I have I can tell this to you little in the coffee break. What they obtained for the straight rods. I don't remember, to be honest. Okay?
Okay, let's thank Jürgen again. And we're calling the next speaker, Professor Roberto Andrade from Bahia.
Okay, can you hear me? Okay. Well, I would like to thank the organizers for being here and celebrate Constantino's birthday in this meeting. It's a real pleasure for me to be here. I will see if it works. Here is the pointer. And then, okay, this is forward. Okay, this is forward. Okay, this is the outline of my talk. I will talk on scaling of mortality in cities across the Americas. Okay, I put here this outline, usual outline, but then I will change this outline and put an introduction. Okay, and this introduction is about Tsallis' inspired work and fun, as mentioned by Ugur in the first day. Okay, how you said to him that he would not be rich, but he would enjoy doing statistical mechanics. So that's the point. So I will say some words about that. Probably, Jürgen, I know Constantino for a longer time than you do, because I was talking to him yesterday, and in 1976, I attended a SBPC meeting in Brasilia, and that time Constantino was still in UNB, okay? And we met at that time, okay? I was already doing my master with Salinas, but I think we met in that meeting in Brasilia, okay? So after that, I had some interactions with Constantino, and I could get some 9 works that has something to do with his work that I said is inspired by Constantino. Okay, some of them have to do with the Q statistics, most of them. But here I have 2 works, one with Suani and another with a student of mine, which is not directed with the non-extensive entropy, but what we call Tsallis scaling on easing chains with longer range interactions, okay? So, of course, I have, and this one is the only work that I co-authored with him. So my Erdos distance to you is 1. Okay, and that was a joint work with Ernesto and another colleague in Salvador. Okay, these are some the first work that I showed to you. This the one of the first works on the generalized Boltzmann-Gibbs statistics, working with the Ising chain. That was then work. This year was a little bit of fun also. Okay, work and fun. I helped organize the celebration of your 70th anniversary 10 years ago. Okay, that gave me a lot of joy too. And I attended some meetings with you. This is one meeting that we were in Japan. Okay, in the Nara meeting, Adrian was also there, Andrea was also there. And from this meeting on, we started doing the series of 4 works together with Evaldo, Fernando, and André André Mauricio, on the thermodynamic formulation of that problem of interaction about vortices, which was inspired. And that among those 4 works, there was where we show how you could provide some insights about thermodynamics and Carnot cycles for that particle on the interacting particles in the absence of thermal noise. And that led me, contrary to my cousin, José Soares Andrade, I do not put some jokes in the, but I permitted that time to put some ideas that was on Simpsons, Homer saying that Liza, to his daughter, in this house we obey the laws of thermodynamics, after she claimed to have constructed a perpetual motion machine, okay? And so to conclude this first part, I say that all of us do this, okay? All of us, we obey the laws of thermodynamics. Okay, Constantino? That was a kind of inspiration. So happy birthday, Constantino. Sorry for the misprints. I would like to say Constantino, okay? So, as Jürgen said, back to work then. This was the title of this work. This work originates from my currently interaction at the center in Salvador of the Fundação Oswaldo Cruz. And I am now doing a lot of work with data related to health. Okay, I thought about bringing this work here to your attention, because here in our community, there have some previous works on scaling in cities. Yesterday, Depman talked about cities, city theory. I know that Henio has already done some scaling of mortality and disease propagation in cities. Tsallis also has already done something like that. And so I decided to put this work, okay? And this work, you see it's a lot of people there. It's a joint work, international collaboration between, in a project that is hosted by the Drexel University in US, okay? And we, at the Fiocruz, we are part of this project. So this is the context, okay? You see a lot of people here and a lot of institutions. And this is the work that we publish in the Science Advances, scaling of mortality in these areas in the Americas. Okay, so here is the outline again, now with C, okay? Data, source, variable, etc., etc., etc. What is the idea? The idea is that cities are complex systems, like living organisms. This was the idea of allometry in living organisms is very ancient. I think that in the 30s, 1930s, they started being appeared. And what is the idea is that in the case of cities, the population, which is a measure of the size of the system, has some social environmental interactions, and these enhance the complexities. And complexity may be advantageous or disadvantageous, depending on specific feature. The fingerprints of this complex behavior can be revealed by scaling analysis, and that's what we have done. All this idea about studying scaling analysis is to get insight of how interactions and lead to complexity, and this complexity can be revealed by this scaling analysis. It is well known that infrastructure as road network and water supply they scale linearly, sublinearly, that is mentioned as economy of scale, as the lungs, the branching structures of branch of our lungs, and also the blood system and so on. So you have this kind of this infrastructure for our body to work. And on the other hand, some socially generated products as wealth, knowledge, but also crime, scaling superlinearly. That means that they grow faster than the size of the city. Okay? So this is the countries. Why the main issue of this work is that although scaling cities has been intensively being worked in the last 3 decades, okay, how the scale influences the health outcomes is still poorly known. So this project where I belong to, they considered a very large number of cities. Cities here, urban agglomerations over 100,000 residents in the US and 10 Latin America countries. So this way we were able to draw more clear influences regarding the mortality, how mortality depends on the with urban. And okay, we provide here, as you see, course and find growth and scale analysis of several causes of death. And see, also we include age differentials, which here is important, the age structure of the population, and coding difference, because if you consider 11 different countries, the way in each country the causes of death are coded to provide reliable data is different. So the data structure was really a key issue of this project. Okay, I will go through that. Those are how the cities are divided. We have 366 in Latin America and almost half between LA and US, 10 countries. Okay, and so we may go ahead. We consider also different causes of death, divided in 6 large groups, 3 disease groups, and 3 injury, what we classify as injury, which are external causes, as you see here. The injuries are road traffic accidents and other unintentional injuries, suicides, and homicides. And among disease groups, you have this CMNN, which is communicable diseases, maternal, neonatal, and nutritional conditions, cancers, and cardiovascular diseases, and other non-communicable diseases. So they are a very huge data set, and then we could be able to extract reliable results for the scaling on this, based on this data. We provided studies for all-cause mortality, then by these 6 difference, and then a final division for 41 fine-grained groups. Okay, the methodology is well known to us. Who scaling are used to scale to work with the scaling analysis. Is basically you you assume that you have a power law dependence, and then you take the logarithms, and then you minimize the residuals, okay? And then now you have to account here that you have 2 indexes, I and J. You have cities. The first index indicates the city, and the second index is related to the country. Because of that difference, how the country, each country changes codes, their data. Okay, but then when we go then to make the evaluation, the minimization to obtain the parameters alpha and beta, then we include these covariates, this alpha 2, which are dependent of, it's a vector, and here are the countries. It's also indicated here, and here is these three terms are the corrections due to the age distribution. Okay, some cities, some diseases affect some ages and other, and so we had to correct this kind of provide this adjustment to call these covariates, and this was some proposed in a recent. We follow this methodology in this quoted here. Besides that, okay, we had the equations were used to evaluate alpha and beta, and we also divided between LA and US cities, and inside LA, due to the fact that Brazil and Mexico have a large number of cities included in the data set, we could perform also scaling analysis for Brazil, for Mexico, and for all other LA cities, minus Brazil and Mexico. So it's a very wide and set of results that we obtained. Okay. As you see, when you go to the results, we also explored the association between scaling behavior and the variance, and scaling behavior and the general prevalence. Just to say, to see how beta is compared with alpha is a measure of the general prevalence with and also the log the standard deviation as a metric for the variability of this phenomenon. So here are the results. We all show for US and Latin America. Here are the all-cause mortality. Okay, those 6 different groups that we showed. The dashed red line, they indicate the equal 1, the slope 1. Okay, and you see that the all-cause mortality for all these factors, you see, are sublinearly for the US, okay, with the exception of these homicides. Homicides well known to scale superlinearly, but suicides, non-violent injuries, and all these scale sublinearly with the size of the population. For Latin America, we see that they have these tendencies, but much weaker, you see it, okay? The exponents here are much closer to 1, that would be scaling linearly, okay, than those in US. This is the first difference that we find between results for US and Latin America. Here, I would like to show also, this is a table that is there of in the work. Okay, then here is the effect of adjusting by age. Okay, these 2 columns, this is the effect of adjusting by age. Here is non-adjusted, here is adjusted. Okay, and also adjusted by country here. Okay, now here there are other transparencies. I would like to show here. Okay, then this part are then for US, Latin America, Brazil, Mexico, and Latin with no in Latin America. But here they adjusted only by age, with exception of this, and these are adjusted by age and countries. Okay, so we have this is the same, this figure is the same that I had shown previously. You see that changes from 9.94 to 0.97. And if you go to Brazil, to Latin America, is even 9.7 becomes 1 here, okay? So it would scale linearly, okay? Also for Brazil, okay? In the all-cause mortality, okay? So the differences are much smaller. There is something that is curious here is regarding the homicides that we saw. They scale super linearly, and they do also when you separate between United States and Brazil, and when you in United States and Latin America, and when you disentangle Latin America for Brazil, Mexico, and the other, you see that Brazil has the largest coefficient, means that the mortality due to homicides in the largest cities is the largest exponent at all in all this in this table. But that is something amazing that in Mexico they scale sublinearly. Okay, that's something that quite unexpected result. Okay, so there is several details that I will not try to bring your attention to. Okay, so you see it's a very detailed work with all kinds of consequences for specific values of the different disease groups. Okay, here is you see the we sorted here by rankings. All ranks homicide stay on the most. Okay, with exception of Mexico, it stays here. Okay, and we did also fine-grained, as I told you. There is 41 different sources of death of causes, cause of death, and then we separate here a difference between comparing sublinear and US and LA. Okay, this quadrant is sub-US super LA, super US super LA, super US sub LA, it's almost always empty, and sublinear US sublinear LA. For these 4 large groups, okay, here is where they coincide, most coincidence is here. The other ones we are related to cause of death are this quadrant is the most populated one, and you compare US to LA. Okay, I will go also rapid here. And another interesting result that we did, the relation between scaling, prevalence, and variance. You see here's the how for those 41 types of results, how is the difference between beta and the intercept alpha, okay, for US and for LA. What we find, negative correlation between beta and alpha indicates that more frequent cause of death tend to be more linear, while less frequent COD, lower intercept, tend to be super linear. Okay, that's an interesting issue that we can do only because you have that much amount of data. For the second, you have a positive correlation between the scaling coefficient and the mean square error. That is a measure of the residues that you obtain. Okay, you have a positive correlation between beta and sigma. Okay, indicate that the cause of death with large variability across cities tend to be more superlinear as compared with those with lower variability. Okay, so there are 2 different kind of results that we obtained. And so we come into the summary. Okay, that's already I have already last time to discuss that, but we show that the scaling they vary for specific case, and there are also heterogeneous scaling between different regions of the world. Okay. Okay, the strong points of the analysis here. Okay. Okay. And here is important, the implication. These findings have implications for understanding the phenomenon of urban scaling and prevailing urban theories. There, the key assumption is that the phenomenon is driven by common universal mechanisms rather than by place-specific effects. Despite that, associations of health-relevant city characteristics, including social, shows that the scaling behavior may differ by domain and by the region. As I call here the attention by other works, particularly this work by Arcaut, which has the title "Construct Cities, Deconstruct Scaling Laws," starts to question this idea that such a universal drivers really apply. In the case of mortality, this is more evident, okay, because it depends on the structure of how these health services are designed in each country, in each region of the world. And although you do believe that there are some drivers which have a universal character, other covariates may influence, and so it's necessary to provide more detailed studies for different regions of the world. And of course, much more studies in this direction are important. So I thank you for your attention.
Thank you, Roberto. Questions, please.
Thank you for your talk. I have two questions indeed. The first one, do you know if there is a minimum number of cities that for which you can apply this analysis? I ask this because I'm doing some analysis with some students, analysis on homicides, firearm homicides in Brazil.
Mm-hmm.
And for Brazil, we find exactly the scaling that you found. Mm-hmm. But when you analyze the states separately, it is not working. Mm-hmm. And the other question is about the superlinear and sublinear character of the mortality. For homicides, it is superlinear. For the other is sublinear, except Mexico. And is this related to the fact that infrastructure increases in a sublinear way, while socio-economic variables increase in superlinear way?
Regarding the first question, okay, we do this choice. For instance, we had 11 countries 10 countries in Latin America. Only Brazil and Mexico are about 100. And so we decided to do that. Why 100 only? Why there were so few cities in Brazil, 150? Because the data set that was organized considered cities above 100,000 inhabitants, okay? And so this limited. And even so, not all cities in Brazil with over 100,000 were in that data set. Okay, so we chose those two only to be sure. If you go to cities with over 5,000 or 50,000 inhabitants, then you can go and include a lot more number of cities. Okay, so it's an empirical. It was a choice based on the set that we had, and. Regarding the difference between with what people, the theory that it's mortality of homicides and suicides has been studied intensively. Okay, the other related to diseases are more difficult but mortality, because this is a very objective way. Okay, suicide is what the usual explanation in the literature is that you have more relationships inside a larger urban agglomeration, and so the social interaction favors give you some support, but otherwise, so may prevent depressions and other syndromes that may lead to suicides. While the violence increases also because of the number of encounters and disputes. Disputes for territories. There are more wealth on the stake, so that the individual interests manifests several times, and this is then would explain the superlinear character of the homicides. That's what.
You more or less already touched, but I was very surprised to see that the suicides is sublinear and not superlinear.
Yeah.
Because although you have more chances to make relationship, the quality of the relationship, we always believed it was worse in big cities. So it seems to be not true.
It seems to be not true. Tsallis has already made this work like that using other data sets, and this has consistently found also that it scales sublinearly.
Okay.
Okay.
And the second question, what about, the bias in the sampling of your cities? Because I believe that as Brazil is so heterogeneous, for example, there will be states or that you don't have the proper data and you have, a bias in the sampling for more organized states.
We have already done at SIDAX, we had a previous work doing only with Brazilian cities. And there we were able to separate, we are not limited to 100,000 inhabitants. And so we did a study for regions, the 5 geographic regions of Brazil, okay? And then we find some differences, okay? Some differences. We analyzed their 4 different, the water supply length. We analyzed the number of jobs in the high technological sector. We analyzed homicides and what was else? I forgot here, okay? But then we could find a consistent, and we also did a longitudinal work, okay? We examined that for several years differently, okay? And so that was stable along the years, okay? And there was some difference, interregional difference, okay? I can provide you the reference to this work.
Okay, yes, eventually a follow-up from this subject that you were discussing. When it was pandemic, we studied the behavior of pandemic comparing different countries. However, there were certain inconsistencies, and we found out that it was the quality of the data that was not comparable from one country to the other. Yeah. And then we compare that with the excess mortality. And then we realized that in some countries, actually, I don't know if they concealed or what they did, but at times, you see, the mortality they declared due to the pandemic was much less than the one observed in the cemeteries, say. So the diagnosis at times is also not well done with the same criteria in all the places. Of course, I understand that with the amount of data you have, all of this eventually is kind of hidden. But do you have a perception on these different criteria among the different geographical areas you covered?
As I told in the beginning, this data was organized by a project hosted in the US. It's called Salurbal, for Saúde Urbana in in America Latina. This project was the lead of the project was Professor Ana Diaz, who she is part of the Drexel University in the US. Okay, and there was a very large team, as you see the number of people that were involved, and they took the project just finished this month. Okay, and they took 3 years to harmonize and select those data. Those data are from 2010 to 2016. Okay, and so it's very the importance of being very careful in this analysis is is crucial for obtaining high precision and reliable. The data, I saw some papers regarding the mortality during the pandemic, and there was I did also some models, dynamical models at that time, and it was very difficult to see how precise those data are. It's very, very difficult. I cannot make a definite statement. It's very difficult, I would say. But that's why I think we succeeded to put this work forward based on this very careful data curation and so on. Okay.
Do we also observe anomalous size dependent on the variance?
Yes, we saw some. You mean this? Here, you mean this figure? Here, what we show here is how the scaling coefficient. Okay. They depend on the. That means if the superlinear the phenomenon is superlinear, there is much scattering on the data. So the residues, there are very much, and so the mean error is larger. While if you have sublinear, the data tend to be more precise, to be better explained by a linear fit. No, it's not a linear. You saw the values that you obtain for the increase here is here, okay? 0.40 for US and 0.31 for South America, okay? Latin America, okay? There are those two.
Okay, let's thank Roberto again, and welcome our next speaker, Professor Suani Pinho, also from Bahia.
Can you hear me? Yes. Okay. First of all, I have to know how does it work. Okay. Okay. First of all, I would like to thank the organizers for the meeting and in honor to Constantino Tsallis' birthday. And I will talk about a topic of epidemic process. I will talk about the reproduction number. That's a very important concept in epidemics process. And but first of all, of course, I will talk a little bit about how I have met Constantino and how I was introduced to this community. And the first point is that it's an interesting coincidence that exact 10 years ago, it was in November 8, at almost the same time, Constantino was in Salvador giving a talk at the university. This is the Café Científico. And it was a very interesting coincidence. The same day, exactly 10 years before, at the beautiful city, not the most beautiful city, but a very beautiful city. And then 20 years before, 2020, most of you was in Salvador, was also in Salvador, in LAMP, the Latin American Workshop on Nonlinear Phenomena. The picture is not very good, but you can see, I don't know how to point, maybe here. Yeah. Aqui? VSC, with VSC here. You were here. Yes, Soares, how is Soares? Robert is here. It's very, the picture is not very good. It's, okay, but I would like to say another thing is that the first time that I have met Constantino, probably he does not remember, I was another undergraduate student in the 80s in João Pessoa, in a school in João Pessoa. And the main point, besides the scientific aspects of it's not a talk, the school, so you have a course, and it called my attention. It fascinates me how your talk is so static. You have it's not only to be very didactic, but also static. You have to you involve people when you talk, and we get the attention, and maybe one of the reason of, in my point of view, of your scientific leadership in around the world, and because you were very involved in your arguments, so we make people involved too. And I was an undergraduate student, and I was fascinated by that. Then we in Salvador, Roberto showed some collaboration with Constantino and some work motivated by him. And I also remind the meeting in Angra dos Reis. I published in the proceeding we published this paper. It's about the power law sensitive. It's very influenced by the work of Marcelo Lira. At that moment, we were working with self-organized criticality. And then some papers that we have done a collaboration with the leadership of Ernesto Borges concerning the formed functions and the formed Q numbers, the generalizations of algebraic structures with 2 parameters, as far as I remember. And it was with this student, Pedro. He's very, but he's not working more with physics, and with Thierry, that's also here, the mathematician in the group. And then it was a very good time because we work with some kind of the deformed functions. Nowadays, we are trying to come back to this subject, looking at some tumor growth. I was talking with Alexandre Martinez about it. And so coming back to the state vision of Constantino, of science of life, as far as I can note, there is a talk a talk that he have done in Vienna, and I was very impressed with the title, like beauty complex is hard to define and easy to identify. And there are during the I get the PowerPoint file, and at some point, like beauty complex can be simple and uncertain. So we talked about maybe built is complex or complex is beautiful. I don't know how to mix this, but this is very, this motivates in some sense, in my point of view, this kind of way of thinking by mathematicians and by physicists. And one aspect, in my point of view, for the build of doing science is, in some sense, I try to have a good aesthetic sense, and maybe exactly to generalize. And this work that I will present here now, it's about a generalization of a method that was proposed about 20 years ago by people who works with mathematical biology, and I was also motivated by the complex behavior in the transmission dynamics of disease, of course. And in fact, it was proposed in the 950s. It was proposed the concept of reproduction number that I will talk about, and then a method to calculate the reproduction number. In summary, the reproduction number, it measured the number of new cases in an epidemic process that are generated by a previous one, okay? It may think about the initial process and also about the time-dependent behavior of this kind of measure. It's an important measure. In general, this measure is calculated based on models or based on data. There are some works that get both of them. And this is the topic of our approach. We tried to get the information about data and to get the information about model. Here, I will talk much more about the method. So I will talk much more about how does the method may be applied to the models, okay? With some data I will do an example in one of the application related to transmission of disease between cities. I will get an example of Rio de Janeiro, the metropolitan region of Rio de Janeiro. But the method that we try is to generalize the next generation method procedures that was previously proposed for estimating R0, that's the basic, the effective reproduction number when t equals 0, but we generalize to the effective reproduction number. So a bit of history. So as I told you before, in the 1950s, the concept was proposed. The idea about the concept is that if it reaches a value that is above 1, so you have an epidemic process. It's lower than 1, you do not have an epidemic process, the main idea. And in 90s, the Dickman, another Dickman, okay, and the collaborator proposed the methods, and they tried to set up a clear mathematical definition of R0, and then they detailed the idea in a book, and also two other people, Van der Driesche, her paper is very famous and very used by the community. They proposed a detailed procedure to estimate R0. In some sense, our work is to extend this procedure proposed by Van der Driesche and Vatman. And then to do that, there are some steps that's very important. Another guy a very important guy in the area, Fred Brouwer, they highlighted the essential concept of infection age. We'll translate infection age in the in the next slide. And this concept, and also in 2006, Valinga and Lipschitz emphasized the role of another concept, that the generational interval distribution for the effective reproduction number. The effective reproduction number is very important because during an epidemic, the conditions change. So, of course, the RT changed according to the condition. If you have a vaccine, you have another situation, and so on. And in 2009, Nishimura and Showa presented some mathematical and statistical properties that's very important too to our work. And now we present a generalization of the procedure based on models and on data, as I told you before. And we also apply, the idea is to have a general method to apply to more complex models, okay? Such as stochastic models, media population models, to investigate different contexts. Okay, this is the most important paper for this talk. It was done by these people and me. Daniel Jorge is now a PhD student in Princeton University. He's a very smart guy with a very sophisticated view how to construct and how to get together data, mathematics, and biology. Now he's in a group of ecology. And then we have, as I told you, the preliminary. This is the concept, the general concept. So the difference that when you get the effective reproduction number, the infection reaches a partial susceptible population with change on time. And the next generation method is based on the idea that the infection process maybe think about consecutive generation of infected individuals, analogous how it's done on demographic generation. People call it the epidemiological birth. And so we can have a matrix that translates the behavior, the dynamical behavior of successive generation. And they have proved that the basic reproduction number may be written as the spectral radius of this matrix, looking at multiplication in M generation. The idea, if you look at a very simple model, such as susceptible infection, removing the model, that individuals who are susceptible become infected by contact, and then may be recovered. The idea, in some sense, is related to the change of the stability, the local stability of equilibrium related of equilibrium with about infection, free from the free disease fixed point. Okay, but when you have a more complex model, it's important to have a more compact procedure to do that. So they proposed the idea, the method. This is proposed by, this is detailed by Van der Driesch. The idea is that if you have a system of differential equations, you can also consider the part of the system that is related to the infective compartment. So you do not look at the whole model. You look at a submodel of the whole model. And based on the submodel, you can calculate the basic reproduction number in terms of two metrics. The first one corresponds to a matrix whose elements are the rate at which infected individuals in G produce new infection in I. So the V matrix is the matrix of transition terms of the compartment. So the eigenvalues are obtained for the free disease equilibrium, as I told you before, and R0 corresponds to the largest eigenvalue. it is applied for very different models in the literature. And I have put an example that you have done recently that's more sophisticated model, for example, looking at the co-circulation of virus in a vector-borne model. You think that I don't know how to put, you think that, you know, where is the pointer? Do lado. Okay, okay, thank you. I tried, but okay. So the susceptible individual may become infected as a primary infection, but and then how does it occur? With contact of a vector who is infected. That's here. Then the primary infected may be recovered for one of the serotypes, for example, or if you look at in this paper, you look at Zika and dengue from one disease, and so it may become a secondary case of related to the other serotype. So you can have a more complex model, and we try to do that with using a master equation and to construct a stochastic model. And looking at a stochastic model, that's important to say that in the secondary infection, you can have a cross-infection parameter from virus 1 to virus 2, for example. And this one may increase the infection or decrease it, depending on the cross effect. So it's a more complex model. And in this situation, you can also calculate using that method, the well-known method for R0. Do not worry about the side of expression, but you can calculate the two possible basic reproduction number, and it is related to the condition probability between the vector and the susceptible, and so on. So it's more complicated. And the other important point is that, for example, if you have a model, a simple model, the basic reproduction numbers does not depend on the initial conditions. But in some situation like that, it may depend on the initial condition. For example, it's very important if you consider that at the very beginning, you have an exponential growth which happen with data, it's important to look at the removed individuals from one serotype. So it may become more and more complicated. There is no immune humans at T equals E0, for example, you come back to a more simple situation. That's very important in the case, for example, that happened in Brazil in 2016, okay? That Zika is introduced 2015-16. That Zika was introduced, and you have a lot of people who have got dengue and is susceptible to Zika. And it's more important, it's also more important when we consider the vaccine against dengue. This is a situation that we are working now. But concerning the effective reproduction number, the main idea is that we can think about a rate of new infections at time t. This idea is from Nishimura, caused by an infected human at time tau that is smaller than t. Then the number of new infections and the reproduction number are given by this. We have a kind of renewal equation. And to count the number of secondary cases, you have to integrate this AT. And if you consider also that there is a probability distribution of time interval that an infection human take to infect secondary cases. This is what you call the GT, the generation interval distribution. So we can assume in some situations, not in all situations, that G depends only on tau, and you can rewrite the RDT in terms of a kind of convolution that you have here. And this variable may be related to the model. It depends on the susceptible, but it may be related to the infective cases and to the real infective cases. And the G tau also is a kind of green function that it depends on the model, on the parameters of the model. So that's the scenario. You have applied this idea. It's not the method yet. We have applied this idea in this paper in 2022, looking at COVID. We look at a model that consider the exposed individual and also the infected, the asymptomatic and the symptomatic infected individuals. Concerning the calculation of RDT, you just look at this part. The other part is related to hospitalization and other things that we analyzed. These two papers calculate the RT, but at that moment, you have not generalized the message, okay? So after that, we saw that it's important to generalize the idea of Van de Driest using the idea of Nishimura, and we try to construct the same idea that Van de Driest did, taking into account the whole time that people are infecting other people. So when you do that, you have the system of differential equation, and you can do the same to take the derivative, and we can do a kind of linear algebra calculation and to take into account the eigenvalue. And due to that, we generate now a matrix that is a next generation matrix that the RIG, and also the generation interval distribution method. In some situation, if you have this simplification here, I get the FI, you can get a number that represents the reproduction number at time t, not a matrix, okay, but a number. But in other situations, like, for example, when we would like to get the influence from one city to the other city, what's the number of exported cases from one city to other city, it does not work. There is not a number, but you have a matrix. Then we applied it to very simple model. I will not follow the details of the calculation. You do all of these steps that I told you before, a lot of calculation, and you do this for example, a CIR model, and you get back some results that are well known. You can see the details in the paper. And then we come back to our model of COVID, considering that exposed people does not infect, and we recover the results. And then we also consider the situation based on data. This is the BT is data. Then we look at just the application to show you the main idea. We look at some cities in the metropolitan region of Rio de Janeiro, is the highest number of cases, and we get the data from mobility, and would like to know how is the influence. We consider the pendular flow of individuals, mobility, and number of cases, okay? So we construct a meta-population model looking at the residence population, the outflow and the inflow, and you calculate the transmission rate for this model, for example, of SIR meta-population model, and you apply the method. When we apply the method, all the steps, okay, that we have done for this, that you have showed for the simple model before, you can get the metrics. So the reproduction number cannot be summed up into a total reproduction number. So you have to get another concept, that the number of exported cases. Then we calculate the number of exported cases. And when we see, for example, a matrix like that, here's the name of the cities. And the main idea is to get the influence from one city to the other city. It's not only based on the flux, but based also on the number of cases in each city. Okay, for example, we can see some situation. Here is the number, the influence of number of infections caused by a count on another one. You can see, for example, the influence of Nova Iguaçu, the brown one, in the other cities, okay, estimating the number of exported cases, not only, for example, in Rio de Janeiro. If you look at this, if you look, for example, at this is the influence of Rio de Janeiro in another city, but here's the influence of Nova Iguaçu, that is also large. Okay, and so we are able to generalize the idea. The method allows us to estimate other key quantities, such as the number of cases that an account generates on neighbor ones. And we consider also more complex scenario. We are applying the methodology to the model of COVID with vaccine. There is a comparison between what they call lake vaccine and all or nothing or non-vaccine. The COVID vaccine, people are considering that this is a lake vaccine that changed the contact rate between individuals. So we are trying to do this calculation from the theoretical point of view, and then to look at the dengue model with vaccine. There are two vaccines, none of them is applied to the whole population as a public policy, but they are trying. This one had problem. It may not be applied to people who have dengue before, but this one may be applied. They are trying to look at this one now. And also doing two other works that's very interesting. Dengue model is entomological parameters of aquatic phase, varying with temperature. We are looking at Foz do Iguaçu data because there are many cases of dengue in places that are colder, that does not occur before. It's a very hard problem around the world. And finally, there is a student, Roberto and me, that is looking at an alert or the system of outbreaks of an unknown and transmitted disease. Thank you very much. This is the group, some reference, and Constantino, happy birthday for you. Okay, thank you.
Thank you, Sony. Have questions here?
Thanks, Suani. Very interesting review of concepts and new ideas. I have a question since I've tried to do some modeling. In even the simpler models, there are parameters that we don't have a good idea from data what they are. So we try to fit, but there's always many more parameters in the model than we can get direct evidence from. So my question is, how serious is that a problem in epidemic modeling, or can we just go forward with a few basic numbers like R0 or R of t?
I think that it's really a serious problem, but I think that you have some strategies to treat this. First of all, is this kind of strategy to separate, in some sense, for example, the probability distribution that are related to the parameters, and other ones that are more difficult, for example, the ones related to the contact rate that depends on the place that, so we get the information from data. This is this, I think that's the best strategy. Another strategy that's important that you have done for COVID model is to consider, for example, the asymptomatic case. The asymptomatic case, you do not have the values of. So the only way is to do what people from statistical physics are very used to do, is to do a kind of how to say, varredura, the word, yes, about the parameters, and to do other kind of methodology of sensitive analysis and so on. I think that this is a mix of procedures to get the idea. Another point is do, for example, what you have tried in the metapopulation model, is to compare. You get a simple model and you get a not so simple model, and to compare the effects and to get the difference and to analyze the effect of this difference. This is one way. This is some procedures, but this is a real problem in the. But I think that the solution is not to consider only data. Okay, people are trying in some situations to consider only data. This is a very, in my point of view, this is a very wrong way to analyze. This is you can get these, you can consider machine learning to analyze other things, but not to avoid to consider the dynamics. This is, in my point of view, maybe I am older, but this is a very, with no direction. You get the data and try to consider the data without, including the idea that the data are not good many times. So we have a lot of subnotification. So you have to mix, in my point of view.
Okay, let's thank again Suani. We are somehow behind our schedule, so I will suggest us to have a short break, 15 minutes break.
Vem cá. Ah, é o presente baiano.
Okay. We are going to restart the section of this morning, and the next speaker is Professor Plastino. Please, Plastino. You missed.
Hola. Well, it's a pleasure to be here to celebrate the birthday of Constantino, and I will talk. The talk is going to be based on some old works, but which I think that may be of some interest today. First of all, well, a bit of history. In the 90s, some of the main themes that were going to be later developed and investigated in great detail by many people. One of the main themes along which research on SQ thermostatistics were identified in the 90s. And so we have long-range interactions, systems involving power law, density-dependent diffusion, edge of chaos, weak chaos, and the microcanonical description of finite systems. As you have seen in the wonderful previous talks, that some of these applications of Q statistics have been explored and developed to a high degree of sophistication. For instance, long-range interactions. Well, we heard the fantastic, the wonderful talks by Andrea Rapizarda, by Alessandro Crucino, by Antonio, and you see that's an area that's been explored by many people and who have done excellent work and great advances in that direction. The same can be said about systems involving power law density-dependent diffusion. So we heard, for instance, on Monday, a very interesting talk along in that direction by Renio Mendes from Maringá. And well, again, in power law density-dependent diffusion, there has been, over the years, great works. For instance, by Professor Sergio Kurilev from Chile, who is here, and by his students, like, for instance, Eduardo La Rosa, who is going to put a poster related to that subject here. And the same, well, edge of chaos, weak chaos, we have heard fantastic works by Ugur Tirnakli and Borges right now, but also previously. They have done great work over the years, lots of interesting developments. And then we arrive to the last one in this list, which is the microcanonical description of finite systems. So part of the talk is going to be focused on this last one, which is has not been explored or developed to such a great extent as the previous three, but still I think that it has some interest for some reasons that I will explain later. But okay. So the SQ microcanonical connection has interesting historical, pedagogical, and conceptual facets, I think. Because of several reasons. First, the Q distributions were already present at the very beginnings of statistical mechanics. So if we read carefully some very early works, foundational works in statistical mechanics, you can identify, it are easily discernible the Q distributions. So that we can say that Q distributions are not exotic. They arise inevitably from basic mechanics. And also, the SQ microcanonical connection suggests an alternative route, still largely unexplored, to explain the phenomenological success of SQ thermostatistics. So, let's give a very brief summary of what is the microcanonical path towards the Q distributions. Basically, consider a composite system consisting of two subsystems A and B, jointly described by a microcanonical ensemble with a total energy AT. And let's assume that the level distribution of system B is quasi-continuous, and that the number of states of subsystem B, which energy is less or equal to a given energy E, grows as a power of E. Under those conditions, it can be shown that the marginal probability distributions describing the other subsystem A, are Q canonical, where Q is related, the parameter Q, the entropic parameter Q, is related to the exponent describing the level distribution of subsystem B, and the temperature, the inverse temperature beta, is related to the total energy and again to the exponent. So in a nutshell, that's the microcanonical path towards Q distributions. So, and okay. That scenario that I explained in the previous transparency, in the previous slides, is not exotic. It's something that appears everywhere or very naturally, and actually can be identified in a paper by Maxwell of 1879, where he considered what we will now in modern terminology we would call the microcanonical ensemble. He didn't call it that way. That the term microcanonical was introduced by Gibbs almost 20 years later. But okay, he was clearly working with the microcanonical ensemble, and he deduced a lot of interesting things. And among those, he obtained the marginal probability distribution for the configuration variables. That is, tracing or integrating over all the momenta, he obtained the marginal probability distribution for the configuration variables, and it's clearly a Q Gaussian. So in this work by Maxwell, one of the first works in statistical mechanics, Q Gaussians are already there. And here, N is the number of momenta in the system he's considering, and then you get an expression for Q given, which is given there. On the other hand, there is a popular derivation of the canonical Gibbs canonical distribution that goes through a Q canonical one, which you can find, for instance, in Feynman's famous lectures on statistical mechanics. In the first pages, there is a derivation of the canonical ensemble, and if you look carefully, you will easily identify a Q exponential there also. The argument of Feynman is basically the same as the one given by the calculations by Maxwell. Well, and okay, following in Maxwell's footsteps, more recent authors have also, unawarely, that is between knowing it, they were also computing and depicting now nice Q distributions. So if you see, for instance, this paper by Ray and Graven, 1991, when I think the title speaks for itself. Small systems have non-Maxwellian momentum distribution in microcanonical ensemble. That's the title of a paper that, if you don't know the authors, you may imagine that the paper was written by Constantino or by any of us. It's always above 1, but above 1 using the convention that the exponent is 1 over Q minus 1, not 1 over 1 minus Q. If you use, so in the other convention would be Q less than 1. That is, it's always with a cutoff. Always with a cutoff. This microcanonical path chills always Q distributions cutoff. Yeah. And in this other paper by Roman, White, and Velasco, also, if you take a look to the paper, you will see very nice pictures of Q exponentials. Well, more particularly Q Gaussians. Okay, and along these lines, I would like to devote a couple of minutes to a paper which I regard as an important one by Barancher in 2002. Barancher was a friend of Constantino, and he did important work on developing, advancing the Q theory. And in particular, he wrote this paper in 2002 with this title, Why Tsallis Statistics. And basically, he elaborated on this idea on the microcanonical connection. And he made a very interesting, I think, a conjecture that this microcanonical scenario may be extended also to non-out of equilibrium scenarios. His idea was that in a system, in an out of equilibrium process, a system consisting of a subsystem of a larger system may be interacting only with a small number of effective degrees of freedom of the rest of the system, and that may lead to a quasi-equilibrium state described by the Q canonical distribution. And this idea of Barancher of extending the microcanonical scenario to non-equilibrium situations has not been explored, but I think that it may be interesting to do that. And among other things, the scenario conjectured by Barancher has some similarities with the process which has been advanced by the famous astrophysicist Lynden Bell called violent relaxation in galactic dynamics. So I think there are interesting things maybe to explore in that direction. And unfortunately, this paper by Barancher is not very well known. It has relatively, and I think one of the reasons that it's a peculiar paper, not only in the sense that the ideas are interesting, but only this paper has a very peculiar property that has no citations. So it's a paper with no citations. He mentions our 1994 paper, but only within the text, not as a citation. And I think that the fact of having no citation has isolated this paper from the universe, because usually one learns about the other people. Well, I mean, sometimes one learns about other people's works because they cite you or they cite your friend, and it's establish a connection, a network of citations. So papers with no citations have the risk of being completely ignored. And unfortunately, that happens with this paper, which I insist, I think it's a very interesting one. Well, it's not completely ignored. It's cited in Constantino's book. So if you read Constantino's books, you will find this nice paper. Okay, I will now give a brief review of some works done by other people in relation with this microcanonical scenario. Some works which there are lots of work, but there is no enough time to mention all of them. But I will select some ones which I think particularly interesting or representative. And well, I like this one by Abid Moreira, Andrade, and Almeida. I like this one very much. I think it's a kind of a paradigmatic example of how a paper should be, because it presents a theory with all the very clear derivations in a relatively general context, and then a very nice and neat numerical verification through numerical experiments, in this case on a change of anharmonic oscillators. They consider a scenario where we have a composite system consisting of a subsystem A. Well, yeah, and the rest of the system is described by a Hamiltonian, which is the sum of various terms. Each one of them are homogeneous functions of the canonical variable of a subset of canonical variables. So that nk is the number of canonical variables appearing in the term hk, and lk is the degree of the homogeneous function. And so they proved in a very nice way that if you compute the marginal distribution of subsystem A, you get a Q exponential again with the value of Q given by that elegant expression involving the number of variables in each term and the degree of homogeneity. So in the case of classical Hamiltonian systems, I think this is the most general formulation of this idea of the canonical scenario, microcanonical scenario. And other researchers have explored and elaborated this SQ microcanonical connection in a number of very interesting ways. I emphasize this work by Ademir Lima, a good friend of all of us, and Deppmann, where they studied in details various interesting aspects of this microcanonical connection for the case of finite ideal gases. And the work by Aquilanti, Borges, Coutinho, Mundim, and Carvalho Silva, which I didn't know. I learned about this line of research on Monday when Walter Carvalho Silva gave a wonderful talk on the application of Constantino's Q statistics to chemical kinetics, and it was a very pleasant surprise to see that they were using in a very sophisticated way this microcanonical connection this microcanonical path towards Q statistics. So I was delighted to see that there was a very concrete and very highly developed application of the microcanonical connection. Well, and finally, I would like to advertise a bit a review paper that I wrote with my father this year on this connection between the microcanonical ensemble and Tsallis theory. Well, unfortunately, we didn't include this work on chemical kinetics because we weren't aware of that line of research. Well, but there are not all is happiness. There are some people who disagree with this, but that's okay because as Vinicius said, para fazer samba com beleza é preciso pouco de tristeza, bocado de tristeza. And so we have people who have a different view on this issue. On the one hand, we have Nauts, which is also a good friend of us, in spite of he has a partially different view on this. Nauts and Bitten, who also revisited this microcanonical connection, and they reached the Q exponentials. Well, it's in the title. They say non-extensivity in the configuration density distribution in the classical microcanonical ensemble. But then they do an analysis, and they suggest that even if the distribution is Q is a Q exponential, the proper interpretation may be that it is maximizing Renyi entropy instead of Tsallis entropy. So they have an argument there suggesting that the proper entropy to consider is Renyi, not Tsallis. But they themselves acknowledge that their argument is not conclusive. So it's an open question. And on the other hand, a more serious criticism is by Ramshaw, which in a sense is also an old friend. Ramshaw published one of the first papers on Tsallis statistics before 1993. In the very first beginning, he published a paper proving an H theorem for a master equation satisfied by Tsallis entropy. But then he raised some criticism, in particular to the microcanonical connection. And again, he says that, okay, the distributions are Q exponentials, but he said something along the following lines. He said, okay, there is a Q exponential, but that doesn't mean that there is a Q entropy. He said that the presence in this particular case, but also in general, of a Q exponential does not imply a Q entropy. And that kind of opinion has been raised by other people, and it's recurrent. After a few years, there is a new paper saying, okay, Q distributions are okay, but Q distributions don't lead necessarily to Q entropies. And that's then what I want to discuss in the next part of the talk. Okay, here is something that we all know, the basics of maximum entropy procedure. When we have it in particular here, the Boltzmann gives Shannon entropy. We have one constraint, and we optimize the entropy. We obtain the well-known exponential distribution. What these people claim is that any distribution can be obtained from Boltzmann's if you use an appropriate constraint. So if you have your probability distribution or density, by the way, I'm not going to distinguish between probability density and probability distribution because basically all that I'm going to say holds both for, oh, okay. Okay, they say, well, anything can be obtained from a logarithmic entropy if you define an appropriate constraint. So if you have a probability distribution F and you want to get F from a maximum entropy principle, okay, you construct this, for instance, this function B. And then obviously, if you maximize Boltzmann entropy under the constraint given by the mean value of B, you get this distribution, which is going to depend on X and the parameter beta, which is the Lagrange multiplier associated with B, which has that form. And it's actually an escort distribution associated with F. And if you put beta equal 1, you get F. So anything can be obtained from Boltzmann entropy if you define appropriately the constraint. But the same happens for any entropy. So what these people claim is actually that there is a basic ambiguity, because any probability distribution can be obtained basically from any entropy if you define an appropriate constraint. That's the core of the criticisms that has been appearing in various papers. So for instance, if you have pure power laws, like that one depicted there, which A is a normalization constant, you have A times n raised to minus beta, and you use a logarithmic constraint that is as constraint the mean value of log of n, and Boltzmann entropy, you recover the pure power law. This has been, for instance, studied in some detail by this paper by Visser. Okay. He also provides some possible justification of the meaning or interpretation of logarithmic constraint in terms of the logarithmic response of perception in biological entities, animals, humans, and what is called Weber-Fechner law. Okay. Okay, but let's consider what I call the entropy optimization game with one constraint. You have a generalized entropy, you have a constraint, and then which are defined beforehand. So you first define your entropy and your constraint. You cannot change them afterwards. Those are the rules of the game. So, and then you have as a given, as input, only the mean value of B. And then you can obtain the distribution function that optimizes that entropy under that constraint and normalization, and you get a distribution function like that, where it's monoparametric because alpha can be regarded as a function of beta determined by normalization. And the function A is determined by the form of the function C appearing in the entropy. Okay. But you can also play the inverse game, that is finding an entropic characterization of a given monoparametric family of distributions. So you start with a family of distribution depending on one parameter. It's only one parameter, beta, because alpha is determined by normalization. And the inverse game is to find a trace form entropy and a mean value that after optimization recovers the density. And what those people claim is that there is a degeneracy in this problem, that it has multiple solutions, but it doesn't. We proved in this paper, this paper from 2007, that if you apply this inverse game to a monoparametric family of densities, of probability distribution or probability densities, there is only one solution. The essence of the argument is that you don't have just one single distribution, but a monoparametric family where you have a parameter beta that covers a continuous range of possible values. If you want to recover the whole family, not just one instance, then in this paper we proved that the solution is unique. That is, a monoparametric family of distribution that has that form uniquely determines one entropy and one mean value. So that the degeneracy of Ramshaw, etc., holds for one instance of the probability distribution, but does not hold for a family. if you apply this inverse problem to Power's laws, well, in that case, for Power laws, actually, the only maximum entropy description with one single constraint is actually the one these people claim is given by Shannon entropy and the logarithm of n as mean value. By the way, this was first suggested by Mandelbrot. And the same happens, of course, for the Gibbs canonical distribution. But if we go now to the Q exponential family, well, in this case, the family depends on two parameters, not one. We have Q and we have beta. But to play the game that I mentioned before, you need a monoparametric family. So we have at least two possible ways. We can regard Q as fixed and B as a variable parameter. And then if you do the calculations, that assumption of fixed Q and variable beta leads univocally to Tsallis distribution. On the other hand, if you keep beta fixed and regard Q as a variable parameter, you end up with Shannon. But in that case, you need to have an ugly thing that is you have a mean value that depends on beta. So that's not what we usually want. And in most applications, the natural thing is to regard Q as fixed and beta as variable, because, for instance, in nonlinear diffusion, you have a Q Gaussian that evolves in time, so Q is always the same, but beta changes with time. So the scenario leading univocally to Tsallis entropy is the appropriate one. Okay, so final remarks. Q distributions are not exotic. Q distributions are inextricably linked to some basic early ideas in statistical mechanics. Well, the microcanonical connection has not been explored in deep, and I think it would be interesting to do that. And once we accept the entropy optimization game, the presence of Q distribution inevitably leads to Q entropies. And well, what can I add above all that has been said before by all people? I fully share the feelings of all of you, but I would like to thank Constantino for his ideas, for his support and his friendship, and also for having created this wonderful community. There are here lots of friends that we may not have known if it weren't for Constantino. I would like to also thank all of you for all these years of friendship and interesting discussions and all sorts of things, including physics, Italian movies. And I would like to end paraphrasing Vinicius once more. So, avanzo, Constantino, maestro y amigo querido. Avanzo, Fernando, avanzo, Evaldo, avanzo, Roseli, avanzo, Sergio, avanzo, all of you, a todos.
Questions, comments?
Thanks for reminding us about the form of distribution for finite systems. I wanted to ask, though, those systems, I assume that they are a priori ergodic, and then that leads to
microcanonical. Yeah. In order for the microcanonical distribution to be appropriate. Yeah.
Because in certain discussions, if I remember correctly, one of the ideas was that Q statistics would be applied to non-ergodic systems.
Yeah. Well, okay. On the one hand, there is the fact that I wanted to emphasize that Q distributions are not exotic. That I like to imagine that if Maxwell have known about all the work that has been discussed here, he would say, yeah, okay, I like that. And he would recall that, yeah, those distributions were in my paper. So I want to emphasize that there is a direct connection with the early works by the but to answer more specifically your question, I would say that the answer to that would be in the direction of the proposal by Barancher. If you have a system that for instance evolves in a non-equilibrium situation, evolves too quickly, and let's say that only has time to interact with a few degrees of freedom of the rest, you may, and also there is the fantastic work on chemical kinetics. They actually they apply very closely related formalism to this microcanonical description, and they have a very good agreement with experimental data in chemical kinetics. I think that probably this chemical kinetic application is also related to the fact that a subsystem is interacting only with a few effective degrees of freedom of the rest.
Okay, let's thank Plastino again. And to end this section, it's a pleasure to call my colleague from Alagoas, Professor Solange Bessa Cavalcante.
Melhor. Mas isso aqui não vai. Eu não falo nem com o microfone, só nem microfone. Okay, good morning. My name is Solange Bessa Cavalcante. I am here because I owe some incentive from Constantino, but my talk has nothing to do with what you are talking here. But I hope to attract some people because I'm going to talk about statistical optics. So, but I am really here to thank Constantino for being one of the few people who made me believe in myself. I'll tell you a little bit about the story, and I'm going to talk a little bit about my work. I put the word stochastic there so that it could be accepted, and I thank the organizers for accepting me, accept my work. Thank you very much, and give me the opportunity to come here and say thank you to Constantino for giving me a trust in the beginning of my career. So, qual é o primeiro aqui, né? It's a bit of timeline, which is very short time, but it was very important. In 1976, I came to CBPF after I was a son of a PUC, son and daughter, filha da PUC. And I decided to come here to do my master's. And I had the chance to see a course by Afonso Gomes, who was a very important researcher. And Constantino was one of the students. I was just graduating from my bachelor. I had just had my bachelor. I didn't know anything. And Constantino was so smart, asking questions and all about the renormalization group. This was in 1976. And then I went to England to do my PhD. And I've heard that Constantino was going to give a talk. And so I was very happy to see someone from Brazil, and was a beautiful talk. At the end of the talk, I went to talk to him. He thought I was English. Did you? He thought I was a British. I don't know how, because I don't look like British at all. But, and then he said, oh, well, let's go, let's have some coffee with the doctors and, you know, all the professors. And I said, I'm not allowed. I'm only a squire here. That's how we were treated, the undergraduate students in England. We were the squires, so I'm not supposed to go in the, not lunch with the doctors or anything like that. And so years later, I went to work in FAO, in Alagoas. I always had this dream of living in the Northeast, beautiful place, quiet, and with a lot of work to do. And we really did. We established a bachelor's course, master course, and doctorate. And at that time, the beginning of the institute, there was nobody in Alagoas. There were about two doctors in the physics department. And Constantino used to go there to give us, you know, energy and good ideas. And with him, I made my second published work, which was this one. This was my second paper published, and it was the only one with Constantino, unfortunately. Maybe after this talk today, I can do something. Okay, this is just to tell you the story. After that, after I published that work, I worked a lot with Marcelo. We had a lot of fun publishing many papers. And then I had two children. And so I had to stop for a while. And then some people came back from their doctorate. They did in England in optics, experimental optics. And they were talking about nonlinear solitons. And I was all excited because I was working with statistical mechanics and nonlinear problems and all that. And I got very interested. And we did this paper, which is one of the most cited papers I have. And I was so excited to do something with the experimentalist. So in this paper, I did the theoretical work. And Arthur Gouveia-Neto, one of professor of our department, did the experimental part. It was very fun because I had to go in the book and look for constants, you know, real constants, real system, and it was very nice. And from then on, I went to Rochester to learn optics. It's the best place, I believe, to learn optics. You have quantum optics, to laser optics, all kind of is the imaging, is the city of the image, or something like that. And I had the luck to work with Govinda Agrawal, and we were working exactly on statistical optics. So I went to Rochester to learn optics and maybe mix one of, you know, I was in statistical mechanics, so I decided to do some statistical optics. And we did this paper, and from then on, I only talk about optics. This is the Paulo Brandão was my doctoral student, and now he's a professor. He's a brilliant guy. Miquel Jacinto is another brilliant guy we have there in Alagoas, and we are doing a nice work. I'm I'm going to talk to you about. I chose a very simple very simple system so that I can be simple here and make you understand at least a little bit what I'm doing. So the system I'm going to talk is about Bragg scattering. And we're going to see power oscillations in this system. This work was non-Hermitian version, and we decided to do a non-Hermitian version, which I'm going to talk to you about what it is, what I'm talking about. So I'm going to talk about non-Hermitian photonics, a little bit about the results, which are very exotic. Here they are exotic, really. And then I will present the work we have been doing recently, which is the scattering of partially coherent light by a PT symmetric medium. It's nice because we are putting together the PT symmetric ideas with statistical optics, which is not abundant in the literature. So it's a good thing to explore. So the problem is very simple. This paper was published by this Russian that he was my postdoc, and this is a Mexican. And this is a very simple and very interesting. The idea is you have a lattice in this direction and a field going into that direction, transversally. So the field goes inside the lattice, okay? It crosses through the lattice. And what happens? What happens is very interesting because it's like an analogy with the Rabi oscillations in the matter. We know that you have a field and a two-state system. And then the field promotes the population to go up and down, to oscillate between the two states. Here we have two modes of the field, of the optical field, and the lattice is the one which make the coupling of the two modes. And so see, if you, in the input, you put just one mode, and then the energy, you put energy in one mode. During propagation, this energy is transferred to the other mode. And it goes like that, just like Rabi oscillation. Only that is energy that it is in one mode of the field, oscillating, the energy oscillating between two modes. So it's very simple. And here you can see, here, you can see what we show here is the red one. These are the peak powers, Fourier peak powers. So we start, if you start here in one, here, see, it oscillates, and you see that the other one gets the energy, and it goes like that. Okay, this is a nice problem, nice analogy. And so and it's a simple, very simple problem. So you can see this is the paraxial wave equation. Here is the amplitude of the optical field. Z is the propagation direction, and X is this transversal direction. So you have a scalar field. Everything is very simple, okay? So this transversal direction you see is just one. You don't have the plane, right? Okay, so you can see here the potential. We call it, let's see, potential here. This paper I just show you the potential. It's like the refractive index for us. The potential would be in quantum mechanics, but for us in optics. And I'll show you in the next slide the idea of the analogy of optics and quantum mechanics to become clear that one is the potential, and then the refractive index is our potential. So here for us, it's like the index of refraction. And in this paper, you saw only this real part. What we did was to include the imaginary part. This means that our problem does not conserve energy anymore. You have an open system. And so the idea of the PT symmetry, I show you also in the next slide.
So long as the degree of hermeticity, I guess you want to say the degree of non-hermeticity.
Here. Yeah.
No.
Yes, the beta, right? The beta. You know why we say that? Because usually everything is Hermitian. Now you start with a little small beta here. You still have the same behavior as Hermitian, but you have a phase transition. And as long, this is the parameter, as long as you increase this parameter, it reaches a critical point. And then something completely different happens. So that's why we say this, you say it's Hermitian as long as this beta is small enough. But if it crosses the critical point, then you have a phase transition. You have a phase transition from the real plane to the complex plane. The phase transition is from the real plane to the complex plane. And you have what we call symmetry breaking. And I'm telling you about PT symmetry because it's very interesting. But you don't have to have a PT symmetric. You can have other non-Hermitian, not necessary PT symmetric that work the same way I'm talking here. So PT symmetric systems are just a subset of a larger set of non-Hermitian systems. Okay, so let's go. See, in quantum field theory, we know if H equals to H cross, then it's Hermitian. And then we say in our quantum mechanics course, energy spectrum is real and time evolution is unitary. So probability preserving. However, Carl Bender in 2007, so it's quite recent, he started with these ideas, and he has beautiful papers. He has beautiful lessons also in the internet talking about non-Hermitian Hamiltonians. And he presents very simple Hamiltonians, and he shows that they have real eigenvalues. So you don't really have to be Hermitian doesn't really non-Hermitian doesn't say that you don't have real eigenvalues. You have problems, yes, with the unitary, because now the system is not linear, it is antilinear. But these things are being people are doing research a lot on that. All this talk started with quantum mechanics. PT symmetric means what? Means that you have simultaneously both symmetry, spatial inversion. Opa! Uma abelha aqui me pegou. Não sei se vocês viram. Aqui. Spatial inversion then x go to minus x, p to go p momentum go to minus p. Que momentum? Momentum sim. In time, x goes to x, p go to minus p. Coordinate and momentum. And I, time, goes to minus I. So if you have both of them, you have x going on minus x, p going to p, and I into minus I. So a symmetric Hamiltonian means that the Hamiltonian is symmetric on this symmetry operation. Okay, so here is the Schrödinger equation. And here is the petit symmetric condition. The potential should be of x should be its complex conjugate of minus x. Already? Uau! Você está me boicotando, bicho. Okay, this is the optical analogy. You see, this is the paraxial equation that I showed you before. Here, the index of refraction, and here is the Schrödinger equation. So we make the analogy, but we have to be careful because here you have a vector, a real vector. It exists, you measure. But here you don't have a vector, but you have a complex amplitude, something that you do not know. Okay, in optics, this slides just to show you that I'm not crazy. Things happen, and usually what happens is something goes on in quantum mechanics. Optical people always make the analogy, make the experiments because they are easier to make than in solid state. So I just put this so that you can see there are a lot of work done on that. This one I just saw yesterday, and I was amazed to see the crazy things. The treat, they have a Q-treat, 3-level system, and see how many people. I just put as a curiosity. And here's the paper we decided to do, which is that problem I showed to you, but with the complex potential. And so it's very easy. We can do numerically, it's a linear equation, easy. And numerically, we use usually a Gaussian pulse, Gaussian beam. And here, a first thing we see from PT symmetric is that you see, here, you see, K here is the wave vector direction. So you have K equals 1 in this direction, K minus 1 in this direction that the optical field goes. Okay, so you can put on K or minus K. When is Hermitian, it's the same thing that I showed, but here you can see that if you use one direction, it still oscillates, but it's different if you put in one direction or the other direction. I'm going fast because Marcelo boicotando me. Aqui. This is the most striking thing, is that now all the oscillations I showed you was for that parameter, the non-hermiticity, less than the critical value. Here we put at the critical value, and we see that the oscillations disappear, and what you have is that if you put in one direction, you have something like diffraction, normal diffraction, as if there was no lattice. And here is even more strange, because you put in the other direction and it goes straight through, as if it had nothing, not even diffraction. We put a Gaussian pulse to show that. So you have this very different behavior. And what we did was to include the stochastic theory and treats the optical field as a stationary process. And working with this cross-fractal density, what we do is to, you see, this is the wave equation. Wave equation here. And what we do is that we put the definition of the cross-fractal density on the wave equation, and we get this another wave equation now for the cross-fractal density. And we have something like a different potential now. This function here. Estou me acertando com esse negócio. Okay, let's move. At the input, we use this Gaussian shell beam, which exists. You can see here from Wolf. I forgot to tell you, but all this coherence theory is based on work of Wolf, Emil Wolf. And we find, the funny thing is that we find the same result with the field being partially coherent or quite incoherent. And we find the same result as we found when the field was not, it was coherent. And we wanted to know why. You see, I put here the result of the non-Hermitian, and this is non-Hermitian, but it's fully coherent. There is no statistic here. And the result is the same. And why is that? And so we decided to study the spectral degree of coherence, which is defined like that. And we find a very important result is that the correlations are induced into an uncorrelated beam by the non-Hermitian medium, which is something we didn't expect. We expect that the medium would modify the optical field, but we never expect that the medium could induce, generate correlation from the medium, from the PT-symmetric medium. And this is not very strange, and I have here an example, which spatial coherence from ducks. And it starts, you see, by saying that it's not appreciated that radiation from uncorrelated random sources, for example, from spontaneous emission, if you have a source which was originated from spontaneous emission, after some time, it can produce a very well-behaved spatially coherent field. And I put here the result they show. Lots of ducks, they fall here all random, in a random way. And after some time, it makes a lot of strange things. But after some times, we see that the water waves becomes quite coherent as it was before. So I'm not very far from what happens around. The idea now is this perspective. May I use Tsallis statistics to study partially coherent fields, to study the properties of the electromagnetic fields. I used to work with the medium, and I work with the fields. So we are interested in properties of the field. And here I end up with my dear friend that I'm sure that I know him a lot before all of you, because we all filho da PUC, sons of PUC, and we had a great time And the last years, I have been working with a lot of friends that I had here in Rio, people from PUC. So we working on solid state theory because of the photonic crystals. We can make an analogy, and people who work with lattice crystals, we can work with photonic crystal. Then I work with disorder. Someone else, Raimundo, work with us. And then on hyper metamaterials, which has to do with field theory, and we worked with Aragão. And now, maybe I should go back to my origins and work with someone in statistics. So thank you very much.
Thank you, Solange. I'm sorry for the pressure. Oh, I can have a question or comment. If someone.
Thank you, Solange. You said that you have a light through a non-Hermitian medium. What exactly you want to say about this?
Very well. But you have a lattice, and you have gain and loss distributed. But it's a lattice. I had now, because you see, our index of refraction is a complex function. That's why we say non-Hermitian medium. Usually use a real refractive index. It's not, it's a complex. And so this brings many nice things.
Last question here.
Very short. So the imaginary part of the describes dissipation of energy from light to the lattice.
Yes.
Oh.
Or gain. Could be gain or loss. And this is very convenient to optics, because optics always have dissipation always, and gain always. And statistical always too. You have to include statistics. So that's why we decide to do that.
Okay, it's time for lunch. Then let's thank Solange again. And we will come
Podemos começar? Okay, let's do it. Okay, good afternoon to everyone. Okay, let's start this afternoon section of the conference. We have 5 presentations, 2 presentations before the coffee break, and 3 more presentations afterwards. The first speaker is Professor Gazot from France, and okay, you have to put.
Okay.
In the pockets, yes, and here close to.
Yeah, maybe that you not forget.
Okay. After 10
Where?
minutes, I will.
20? You will tell me 5 minutes? Okay.
So you have 5 to complete and 5 for.
Okay, okay, good. Ah.
Está organizando
Can you?
file en internet para que todas las personas puedan ahí poner todas las fotos. Así todos pueden compartir.
There is what?
No final da sessão eu.
N is a numerical factor.
Eu já vou começar.
You can
I
see
already
the-
announced.
Yeah, pure number.
Okay.
I don't know, maybe the observation will give me the pure number.
Okay. So let's start then.
Yeah.
You can.
Okay. So thank you very much for Constantino and all organizers to have invited me for this very nice conference. I learned a lot. It's not my field really, but I had the privilege to publish a paper with Constantino a few years ago about the Q triplets. Yeah. And before starting, you know, the science, first, before just I want to focus on this sentence I found in a recent paper by you. Further senses along which SQ or other entropic functionals will be unique are certainly welcome. So it is in the spirit of this statement I'm going to give this talk. And also, I would like to remember that we met for the first time officially. I think I am the eldest person here in January 69.
69.
Yeah, we started to, no, 68, maybe, I don't know, maybe, but maybe. In 68, of course, you can see me, but I could not find Constantino, maybe this one. It was one of the first student demonstration, yes. Yes, in Paris, yes. So you can see here, you have an example of not a black box, but black glove. I don't know why I put the gloves black, I don't know. Okay.
And what is the other arrow there?
I'm trying to find you. I could not find there, so maybe you are under the helmet, protected. Anyway, in January 69, I think we met officially with Professor Yvonne Henault. And there was, if you remember, Janet, Madame Garnier, Madame Barbeza, Camoun. You remember Camoun? Yes, Faton, maybe? No? Oh, not still Alzheimer. Okay.
So this work has been initiated in September, and it was precisely motivated by your invitation. So if I am invited by Constantino, I have to find something about Tsallis entropy. So I published in 97 this paper with Sandro Graffi. It has been quoted not 0 times, but just once, except by me, of course. Bollettino, la Unione de Matematica Italiana. And also, it is motivated by this paper in 94 with Jacques Brosse and Ugo Moschella, and this one was quoted a lot, actually, by this book, little book, which is not easy to find. I have a copy. And of course, concerning the Deuterian material, I'm going to describe, not of course comprehensively, but just giving some idea. We published a book recently in 2022 with my collaborator, Mohammad Enayati, Hamed Pejan, and Hanong Wang. Okay. So I will just give some words about temperature, heat, entropy, which produce of a lot of debate, a lot of discussions. Okay. And afterwards, I will describe what we call the Maxwell-Güttner distribution. I borrowed the material from the book by Singe. And afterwards, I will give some description about De Sitter spacetime. And at the end, I will show that in De Sitter, this distribution called Maxwell-Güttner actually is precisely Tsallis distribution. So in September, I was trying to put in order some books in my house, and I found this old journal, Les Cahiers de la Physique, at that time in 48. At that time, you know, most of the French scientists were writing science in French. And I put this the translation. And the first article was an article of Louis de Breuil. And Louis de Breuil actually was the chief editor of Les Cahiers de la Physique, 48. So just, I don't want to read, but you can read very fast, that it proves that entropy in the relativistic context should be constant. And in the paper, I give just before a slide about the problem of relativistic temperature, relativistic heat, and so on. And there is 3 schools, even 4. For one school, which was initiated by Einstein, by Planck, and also de Breuil, and so on. If you go from one inertial frame to another one, which moves with a velocity v, with respect to the relative to the first one, in that case, there is a covariant transformation of the heat here and of the temperature by the factor gamma minus 1. Gamma is a traditional factor, which is here. There is another point of view. There was a lot of debate during essentially the 50s by Haute, Argelès. No, it's not true. It should be in the other way. And there is another school which tells Landberg and so on, nothing changed. Okay, in this talk,
You can add there the paper by Evaldo and for the third one.
the third, okay. But anyway, I will follow this one, this point of view, okay? The first one, the first. No, because if I follow the third one, I have to leave the room now. Okay, this is a demonstration by De Breuil in one slide. Okay, you have a body, proper frame R0, total proper mass M0, so on and so on, with good conditions. And if you consider its motion, it's if you consider the body from a frame which is moving with respect to proper frame of the body, if you consider that, and if you want to keep the velocity in that frame, the velocity of the body constant, in that case, you have to provide the body with not only heat, but also work. In order to, in that case, you change the energy, the time component of the energy. Okay? If you consider that from the point of view of the frame where the body is at rest, there is no work done. So in that case, there is only heat which is provided to the body. You compare both and you get this relation. And if you demand the entropy is constant, in that case, for the temperature, you have exactly the same transformation. This is it was done in a 3 or 4 page by De Breuil in this paper. So I adopted this point of view. Yes. I don't know, but okay. So let me see, because let's fix the notations. So now I consider Minkowski spacetime, and my notation will be for a 4-vector event. This one, okay, I adopt the metric plus, minus, minus, minus. Of course, you know, 1/2 of the people adopted the other sign, and the things adopt imaginary time, which is more complicated. Anyway, so for any 4-vector, I put underline. Okay, so here it's for momentum for a particle in a gas, for instance, and here it's something which is connected with the geometry in order to understand the reasoning by singe. I don't want to insist because that becomes very technical. So anyway, because I will give a summary of all that just at the end of this part. Okay, just examine the following situation. We are in a gas, in a fluid, and you consider from one point an infinitesimal volume limited by null cone, causal cone. So if you have particle entering this volume, it should go through this infinitesimal surface, okay, because of the causality. Okay. So now you pre-assign the number, the population number in function of distribution function here, so which is proportional here in this volume, infinitesimal volume, to d sigma and to the surface element, the projection of the surface element along a surface on the surface d sigma along a unit vector in Minkowski. Okay, so d omega is the element of your phase. And also, there is something which is predetermined coming from the energy tensor. The flux of for momentum across d sigma is given also by this relation, which involves the distribution function. Okay? So now, the most probable distribution functions at m, all that is infinitesimal, is that which maximizes the following entropy integral. Okay, so you have an integral on the momentum here, you have the distribution function, and you define this entropy and log the n. Okay, times minus d sigma. This is Eutner, but it's yes, but I use the description by Singe. I will reach Eutner like this, okay? Because if you make a variational calculus, precisely you get Eutner. With here a constant, but not a function of the events, and here the momentum, the four momentum, here and here some four vector which has the dimension of the inverse of a momentum. Okay, and in order to find all that, of course, you use constraints, corresponding to the integral of K mu, the average of K mu, the average of K mu. Here you have numerical flux for vector, and here you have the density of the tensor density, the density tensor. And if we had the conservation of the n and T mu, we are able to find everything. So everything, well, here we have the distribution, Eutner distributions. So here you have the exponential minus the dot product in Minkowski of two four vectors. Lambda is the mean velocity of the fluid with modulus C, momentum, and here what you have, you introduce Kv, Boltzmann constant, and the absolute temperature, which is defined by this expression. Okay. This is a relativistic invariant, this one, of course. Okay. And the appearance of the Bessel functions comes from the partition function here, which is also a Bessel function. Okay. And of course, if we consider the Galilean limit, that means this energy, temperature energy, is a lot smaller than mc squared. In that case, we go back to the Boltzmann-Maxwell distribution. Okay? So, okay. Yeah. It is not exactly. No, because the Eutler, it was only the scalar, the time part, I think, for Eutner. Oh, I think, okay, we will consider. No, I follow strictly Singe here. Yeah. And here, now I follow a more recent paper by Wu, here, the 2009. He introduced what he called the coldness, which is a four vector defined by this expression. Okay, in order to have this expression here, beta is something which has a dimension inverse of the momentum. Okay. Let's go. Here you have a summary of all that. I prefer to, because it's not, it becomes very technical at a certain moment. So, Eutner distribution in the Singe sense, okay, with four vector here, which is the coldness, relativistic coldness. Here you have the momentum. Momentum, you are on the mass shell. Okay. And this coldness has a time component, which is here, and which is positive, time-like, and a vector part, a space part, which is defined by a fluid mean velocity divided by kBTA. TA is a relation with the invariant provided by beta. So now I go to the De Sitter material. We have to go fast. So just let me describe very rapidly De Sitter spacetime. It is a manifold which is the deformation of a Minkowski spacetime with constant curvature, and you can describe it as a hyperboloid in Minkowski 1+4. Okay, so here an element of this De Sitter spacetime is fixed by this pseudo-sphere relation with radius r. Okay, and r is given in terms of the cosmological constant by square root of 3 over lambda. Lambda? This relation? Yes, because it's if lambda exists, it's positive. It is in that case you have one interpretation in terms of energy, dark energy. I don't like. Another interpretation, it's a constant. It gives you the curvature of the spacetime. That's all. Okay, so this is the representation. Here you have a parametrization of element on this spacetime. And of course, if R goes to the infinity, with this parametrization, you will go to Minkowski as a tangent spacetime at a certain point of the hyperboloid. Okay? You can do that at any point, of course, because on the hyperboloid is like a sphere. Any point is the same. Okay, so now you have in De Sitter, what is the equivalent of the plane wave? It is this kind of expression. Up. Okay, and you can see it's a binomial approximation of exponential. So here you have the dot product on De Sitter. This belongs to the null cone in Minkowski 1.4. Okay, and if you parameterize this 5 vector in the null cone, actually that corresponds to the 4 momentum in Minkowski. Okay, and so here you have, when we go back to Minkowski, first tau is given by -3/2 plus I nu. If you want to have the equivalent of plane waves, that means solutions of the equivalent of Klein-Gordon equation in De Sitter, you get this expression here, and with tau is equal to -3/4 plus I nu. Nu is a parameter, real parameter, and if you want to go by contraction to Minkowski, what you have to do, you have to put this relation, nu is equal to R, or if you prefer, MC over h bar square root of 3 over lambda. Okay? So h bar, of course, is present, and lambda is present. And taking the limit, lambda goes to 0, the flat space-time limit, you go back to the ordinary plane wave. Okay? There is here, I skipped that. What is interesting concerning this famous plane wave, if you want to have a completely causal description of propagation in De Sitter, you must introduce analyticity conditions. And if you introduce analyticity conditions, you extend to a complex formalism, complex environment. And in that case, what appears a kind of Hawking temperature. Hawking temperature is given by this expression in terms of lambda, and of course the rest is purely thermodynamical and quantum. H bar, C, KB. You have actually, what is very interesting, you have the presence of 4 constants here in order to define this constant. Okay? So here you have a summary for the ITER. And yes, and I go now to the last part. So now I'm going to introduce the deformations of precisely of the Hüttner-Maxwell distribution by following what I know, what I found with the De Sitter plane waves, which are binomial approximation of the exponential. But for that, I have to introduce a 5 vector, which a 5 vector which extends the coldness. Psi is a 5 vector in the null con in Minkowski 1 plus 4, and B is a constant which kills the dimension here. Okay, here you have the 5 coldness with a parametrization, and for large B, this parametrization will allow me to go back to the coldness here, plus here the last component is B. Okay? So I made this kind of almost finished. In order to control completely the contraction limit from De Sitter to Minkowski. And finally, what I found this distribution in De Sitter here, where Q is given by expression where you have that the H bar and C and so on. So là, just a scenario of the result. P is the constant against the time to calculate. The constant again I should calculate in terms of different functions, or that is calculated. Oh! But you could hear me? Sure? So, so this is a result, conclusion. If we have a cosmological constant, and if you adopt the first point of view from Einstein and De Broglie, you know, this first point of view, in that case, the Tsallis distribution is necessary. Thank you.
Thank you, Professor Gazzot. The session is open for questions. Evaldo?
Hey, Jean-Pierre. It's funny because distribution obtained by Hüttner in 1911, he has a prefactor, gamma 5, before the exponential. You didn't find this factor here. So distribution is not exactly Hüttner distribution.
But I didn't.
Fringe distribution.
I tried to go through the paper by Hüttner, but it is in German, in Gothic letters.
Yes, so in German.
I use some Gothic.
I have the translation of the Hüttner paper. I can give you.
But actually, there are also afterwards paper by Van Danzig, by Taube, and all that. Some paper were published afterwards following this direction. Yeah.
But
Eutner light, yes, I know.
but people have done many molecular dynamics simulations of this kind of distribution, for example, Eutner distribution in the last few years. And do you know if they have done molecular dynamics simulation with this expression of Singe? Because I don't know. No.
I don't know. But of course, because we had a discussion, if you make simulation at high energy, of course, we have to be careful because in the relativistic domain, you should remain anyway in the causal cone and so on. So you have to be careful when you use a simulation by respecting, completely relativistic invariance in Minkowski. But I think it will be valuable to do the same kind of valuation, of same kind of prospection with this kind of distribution. And everything is given. B actually disappears with before at the limit, so it's not the only arbitrary term which appear here. It's this numerical factor here, n. M is a gas. It's the mass of the particle in the gas. That's all. It's yes, of course, yes, yes. No, because the Eutner distribution you introduce. Yeah. So.
Any further questions? So let's thank Professor Gazeau again.
I didn't think. Hoping to.
Okay.
Again in 10 years.
Let's do our best. Next speaker then is Professor Vogel. Okay, Professor, after 20 minutes, I will time you to have time to.
Okay, and how do you operate this?
Yes, here it is in forward, backwards with the slides, and here is the pointer.
Where is the pointer? Over there.
Yeah, there is the pointer.
Okay, I'm all set, I guess.
Okay.
Okay, thank you for the invitation and the organizing committee. I'm very glad to be here. I was in Angrados race 20 years ago already. And then 10 years ago, I was here. And now, again, I'm here. So I hope to come in 10 years' time again. But I'm beginning to worry because, as I see, you see, you are beginning to contribute to the global warming. So, okay, Constantino, I've been very glad to share all this journey with you. I remember the first time when I met you was one of these Latin American meetings on solid-state physics. I don't remember when was that. It was the end of the 70s, I guess. And you came from somewhere with some percolation ideas, and you gave us a short course on that. And we were all very enthusiastic because for most of us, that was the first time we heard of this percolation theory. And from there on, I've heard so many interesting ideas of you that thank you for that. Okay. So in my talk, I will have two parts. The first one, hopefully in about 10 minutes, I will review some definitions, and I will use a very known model, well-known model like the icing or easing model, whatever you want to pronounce it. And just as an excuse, there will be no new results. Of course, there is just an excuse for definitions. And then I will turn onto something new in geophysics to explain some earthquakes. And as you see, I have several friends from different parts in Chile and in Spain, and they are all sending you regards. And so let me just go to the easing model. And I just take a lattice like this, and these are fixed magnetic moments or spins, and they can point up or down because of internal anisotropy of these pieces, and they can interact via exchange interactions just to nearest neighbor. This is the usually easing model, and you just go and ask if they want to turn around, and if the energy you get is less than the one before you had there, then you accept it. And if not, you just toss a coin, and with Metropolis algorithm, you give a chance that even if the energy balance is not favorable, you still accept it. And you do that L squared times, and you call that 1 Monte Carlo steps. And we will deal here with 120,000 Monte Carlo steps to equilibrate. And then the next 120,000 Monte Carlo steps will be recorded for the measurement. And once you have that, at the end, you will have an energy for that temperature. And if you have the energy, you have the specific heat by derivation. And if you integrate that, you have the entropy, and provided you need an integration constant. And you also have the magnetization, because you can add all the magnetic moments and have the magnetization. And if you have that, you have the magnetic susceptibility. By the way, you can also get the specific heat by fluctuations like that of the energy. So I assume this is very well known for most of you. So this is just reminding things. And then once you have that, you have the energy there, the first derivative, the specific heat, and the integral of this, as I said, is the entropy. Okay, that's the classical things. And here you have the magnetization. And let me begin now from higher temperatures. You come here, and magnetization is 0 because you are over temperature. So it's just fluctuating everything. And as you approach the critical temperature, you see, you begin to have this kind of telegraphic signal. And finally, it goes positive and stays there. Ergodicity has been broken. And this is an additional fact to have in mind, ergodicity breaking, because then you see half of your states are not available to you. And this is very important to remember, because when I presented the picture in energy, everything was possible. But in reality, you see, not all the states are usually possible, and you have to deal with that. And what is channel entropy for my purposes? Well, I have these simulations, 120 records, registers, and I then built an histograms recognizing the energy of them, for instance, and the frequency. I can have an histogram. And then I can calculate the probability for that distribution, the frequency of the total number of registers. And with that, I can get an approximation to this channel entropy within these limits of having 120,000 records. And I have the probability obtained this way, and the log of it with this minus sign. Or it is in microstates, or can go over the levels, considering the degeneracy. And you have, of course, a normalization there. So that's one of the things we are going to be using, channel entropy. And this is what we have introduced. And I will be spending some time here, because eventually not all of you know it, but it's something we have been proposing. What is mutability? It's to do with information theory. It's the same records we had before. And let's take all the bytes, all the records and wait, and we have W bytes. Then we compress them and get a map of it, a new file, and that weights W star bytes. Mutability is going to be this empiric relationship, which is just a ratio W over W. So it's whenever you have lots of repetitions in your original file, this is going to be low value. And when you don't have repetition, all of values are different eventually, this is going to be a large value. You can use any compressor to do this compression to get W's, but none of them give the same results. So you have to go through an optimization process. And this is a definition. We have used these symbols before, but this is the one is remaining. Since we did some simulations since we did some simulations in the Grand Canonical Ensemble, we dealt with the chemical potential, that we had to change that. So I said that not all compressors give the same value. And here you have, this is the first thing we have. We use the basic 2. And this is 3-dimensional Ising model now with a critical temperature 4.51 almost. And okay, you see that it's getting it. This is in growing lattice, cubic lattice. However, you realize that you see when it goes from here to there, it's not discriminating anymore. And on the contrary, it's kind of reversing. And we were a bit stuck because of that, until we decided to create our own compressor, which we will call word length zipper, because it's actually using a specific length in the change of information. And we look at that in the precise positions, because we want to recognize physical information and not just mathematical coincidences. And when we use that, you see, everything goes in place. So this is, from now on, we are going to use from our own creation, this compressor. And that was, you see, long ago. And that was helped by some collection of good students I had those days. And you see, here I compare our compressor, which is a black one, the one I use before, the red one, is 2, and the usual one probably you use, which is RAR. Please continue to keep using RAR if you want to compress photographs or whatever. It works beautifully, you see, it compresses a lot. But I'm not interested in large compression here. What I really want is to have, for the same thing, a large contrast. And so you see here, they start at that temperature, basically the same value. But the black one now, at this temperature, when it's chaotic, the system is compressing less, because it's actually saying all the values are different. This is chaos. So this goes very high, while this other one is recognizing accidental coincidences. So we stick now to this one, WLC, and we have it available. Most of the time, right, unless you invoke the other one. You have to invoke the other one. Right. And the WLC avoids accidental coincidences. So these are results for the Ising before we turn into earthquakes. So this is, I go back to the 2-dimensional system I started with, and you see mutability is black, Shannon is blue, and they go very, very close. Differences are very small. Very soon you are going to understand why is that. But then what we did is we took the same records And we order them, we sorted it from lower values to higher values or vice versa, and we get is a red one. So this is something that no other entropy has it. I mean, we can, with this mutability, we can have kind of a minimum entropy in this way. And this is for magnetization. Remember, we said that we had that, we could recognize that information as well. And here, you see, this is Shannon. This is a mutability with the records as they were produced. And these are the sorted records and after that compressed. Then it's clearly, as I said here, it's clear you are dealing with the after the ergodicity breaking, and you are dealing with magnetization here, and you have separate answers. So I want to close this first part, which was an excuse to introduce this definition: mutability complemented by an appropriate information recognizer. WLCP is not the only one, probably, can give information similar to an entropy for a series representing a property of the system. Different properties of the same system can be evaluated one at a time. Energy, magnetization. Compression of the sorted file renders minimal mutability. So now I'm going to go to a list of things we have done. We have done the Q-colloq model. Q is a generalization of the Ising model. In the Ising, you have 1, 2 positions. Q is 2. This is a capital Q, is not your Q, Constantino. So when you have large Q equals 3, you have 120 degrees, 240 degrees. And this is the possible orientations of that field. So we have done that. And we have done the position of rods on square lattices. And this is the contact with the talk by my colleague Jürgen Stilk this morning. And when you pointed out, this is the contact. We continue to do that. And now we have Diego Massa in Pamplona doing the experiment for that. So eventually in the future, I will be reporting some news from that. And we also apply it to blood pressure. There are some references there in case you're interested. We have also worked with silos that get clogged. And the way when they approach the clogging is there are instabilities that we have described, and we have a paper in preparation for that. We have also applied it we have also applied it to ramps in the wind energy productivity with my German colleagues, but I want to apply it to earthquakes now. I want to hurry up because here this is the central part of the talk. So this I'm listing here 3 papers that where we have done it, and I will go directly to the applications. Let us define a seismic system. This is all going to be related to the large earthquake 8.1 in northern Chile, Iquique, on April 1st, 2014. There is, the seismologists talk about catalogs. In the catalogs, they list the earthquakes with all their characteristics after they run the report of the last station. And so we are going to work with that catalog. And that is filter number 1. Because the same seism could be described by the different catalog. This is supposed to be the best catalog for this part of the world. And filter number 2 is going to be the geographical position. 18 to 24 south, 16 to 72 west. I will show a map in a minute. There you have it. This is the globe, and we went to the northern part of Chile, and this is the rectangle I was just saying. And here you see these circles are the earthquakes. The larger the circle, the larger the earthquake, except for the largest ones, which are the stars. And the least of 6.3 and larger are these that are here. This is 6.3 and larger. And here is the 8.1. If you want to search, this is the first one, 6.6. You can find the color that corresponding is the central one over there. And then comes the 8.1. So you see, this was the first one, that is the second, and the other one is going to come as the third one. You realize that this was holding the thing. When this was broken or whatever, then last one, this one was resisting, this was broken, and then this one collapsed. And all the other ones, you see, they are like three loops. This is clearly attached to that one, these are here, and these others are here. I'm looking at just at the green ones, which are those that follow in magnitude. And this is what I want to study. This, I already filtered here within the rectangle. Now I'm going to filter magnitude. And to filter magnitude, what people do is this Gutenberg-Richter analysis. They have the magnitude here, and they have the log of the frequency. And they have this figure. Look at the red one, that would be enough. And this is what the largest curvature here at around 2.2, and the expert said, from there on, there is this straight line in this log scale, and that is what we want, that is representative for a nice distribution, and this is the distribution we are going to work with the minimum 2.2, and we are going to set the maximum at 6 point whatever. Doesn't matter too much. And that is filter number 3, the magnitude. And now we look at the depth. And this is now depth from 0, surface, and you go 10 kilometers, 60 kilometers underneath. And if you look now at what are within this rectangle, and you see from minus 68 to 72, but you pile up all the others, the other coordinate, which is the latitude, and you just pile down over there. You have here sizes are omitted, just green points for all of them. You realize that, you see, that this part here is way underneath the continent. So we are going to neglect that, which is basically this. You see, there is a correspondence there, and we are going to filter with seisms over 70 kilometers, and this filter number 4 leaves us with 10,640 events. This is a filtering path using this catalog. And now we move to the analysis. And we are going to handle the data, discrete magnitudes, and time intervals. And we will use our techniques. And then we are coming to the calculations and the results. First thing done was we calculated to this sequence Tsallis entropy, the usual definition, which you have seen already. And then you have these 3 conditions that Angelo Plastino was mentioning early this morning. So you see these 3, you combine with Lagrange multipliers. This is just the definition with the probability and logarithm. This is the normalization, and this is referred to the average value. Since you have before the Gutenberg-Richter, you have all the parameters to do this. You have the M max, you can have the average, and then it's not an easy job, but people have done it. And here, this is I have to say that when my friend Antonio Posada did this for this catalog I just showed you, what we got for Q values were basically all close to 1.7, a bit more, a bit less, but 1.7, great. And but some people before, and then the calculation for different areas in the world, and you see they get to 1.8 and as low as 1.48. So in earthquakes, Q is usually large, 1.7 at least. This is what we have found. And Shannon entropy, you already saw. I don't want to say anymore because this is a central part of my presentation. I want you to consider these 50 values that are here, 50 records. This is actually just before February, beginning February 1st, 214. And they go like that. Here is the same values that are here, 2.4, 4.0, but 200, this is just the same ones in blocks of 10, so they look larger. How does WLC works? The weight of this is W, as I said before. And this is the map. This is how WLC works. So this first value, 2.4, is at position 0 because it's at the origin. Okay. And if you go 18 positions, so you have 10, and you have here, and you get here, you have 18 positions. After that, you get it again. And then you have it again 10 positions. Refer to that one right here, underneath 10 positions from there to there. And you start constructing this map. But you see, what is the trick? That you always look at the previous position. So all these numbers are small numbers because you take the intervals to previous. And that's the reason why this is going to be of smaller weight than before, and that's W asterisk or star. But then you can count to the right the frequency. The frequencies are ready because 1, 2, 3, 4, 5 times 5. The comma means repetition. 44 repeated immediately twice, which is somewhere here. 4.0 is here. The repetitions are, and the number of repetitions go after the comma. So here you have the frequencies. And if you have the frequencies, you can calculate the probabilities. And then you have Shannon. And you see, with those you can have Shannon. So Shannon, you can get it as a byproduct of calculating mutability. But if you go before, here you have the history. This is range with one value. Having a mobile window of 256 events. Next one is 512, 1024, and 2048. And these are the years from 2007 to 2015. And you see how before, this is a large earthquake, which are represented by these symbols there. Just before, there is this enlargement. So Tsallis entropy is telling something like 2-3 years before the main earthquake. How about mutability? about 3 years before, Tsallis entropy is enlarging, is swelling before the main earthquake. And the same is happening for the mutability. But the opposite here is a minimum that is arising a couple of years before. So somehow the Earth is saying something. Then my friend Antonio Posada from Spain just said, why don't we look just a few days before, oh, sorry, but a few days before, 80 days, 40 days, 20 days, 2 days before. If you look at this tail, you see, it's growing there. So we get an announcement, and we have a GIF there when you can follow here, 80 days to Maine, 40, and you see how it's growing to the right. I'm going to let it goes after, and it goes to the aftershock. I'm going to wait for the next cycle so you realize half a minute and I'll be done. And there it's going, you see it's going to the right, and okay, and that is done. We can also do it by intervals. Since my sermon is getting nervous, I will not say anymore, but with intervals between consecutive earthquakes, also mutability recognizes this behavior, as I said. And these are the final conclusions. Tsallis entropy grows a couple of years before a large earthquake. It's energy accumulation. Mutability decreases a couple of years before the large earthquake because only small quakes are left. And Tsallis suddenly decreases at the time mutability suddenly increases days and hours before a large earthquake. This is not tested in other worlds of the planet. This needs to be tested, but at least if it is a good hypothesis, hopefully we can get somewhere. Thank you.
Thank you, Eugenio. The section is open for discussions. Evaldo, the perguntador.
I believe in 62, no, Chile had a extremely large earthquake, no?
Oh, yes.
62 or 61, 62.
In the list of the 10 highest earthquakes,
yes,
since there is record, we have the first one and the sixth one. We have all kinds of medals.
It's not good to be in this, in this list, but anyway, you have the recording of before this very large earthquake in 62, so you can see if it happens there.
Oh, very good point. You see, the quality of the data has changed substantially in the last. You need lots of stations to get this catalog I mentioned, the IPO catalog. In the 1962, and the 1960 earthquake, there were very few stations. So the magnitudes and the times, especially the magnitudes, are not very precise, Evaldo. In the last, during this century, they are very reliable for present accuracies.
Okay.
Thank you for the nice talk, Eugenio. Have you any contact or dealt with the data from Japan?
Oh, yes, good question again. Because you see, if you go around the Pacific, let's go from Chile again, from the Pacific, go north, you get to Peru, and this seismicity continues there. And you go to Ecuador, and in the list of these 10 largest earthquakes, Ecuador is 4th or 5th, I don't remember. And you continue, and in Mexico, you know how it's Mexico from time to time. And you continue to California, and you know in California, you get to Alaska. Alaska, in this list of 10, I think it's got 2 places. And you then comes down the other side over Japan and Indonesia and all that. That is, they call the circle of fire. And that, I don't know why they call Pacific Ocean to this ocean, but they called it Arial. And the whole thing is moving. And this is the scheme on the one plate goes underneath the other one, which is the subduction. And yes, Japan is a possibility. But before that, we're going for California. Because in California, there is the subduction process in San Diego, and then San Diego and Los Angeles. And then in the north, San Francisco is a fourth, which is different. Huh? No. And then you have Blanco on the left, which is a mixture. And there are three different sources in California. Okay. And I'm going to stop there because I could continue.
And the second question is, well, earthquakes are not the only unpredictable kind of phenomenon that we have. We have some others. For example, the crashes in the financial values and things like that. Have you tried to, to apply the things for other phenomena?
Yes, in that list, I didn't mention everything, but we have done it, but I didn't want to mention it because you see, two talks from now, an expert is going about the econophysics going to speak, so I don't want to to say much. But let me say that yes, we had an application to the stock market, and it worked. And in one of the runs that they had, unpredictable ones, because that was done by a machine, we got it. But that what about cardiology? Oh yes, yes, we have done. A student did a thesis for that, and we have succeeded. We did that with the cardiologist. We can somehow predict. No, not predict. We can classify. That can help. Dead and alive. With this kind of friends, I don't need enemies.
Okay.
How does this one get divided equally?
No, exactly. I mean, I do have that. That is the thesis of medical physics in my university, and we have it published in the journal. If you're interested, I can send you the paper.
Okay. Oh, people, let's thank Professor Holden again. We come back at half an hour. That means, okay, it is 15:40, 10 minutes after 4 o'clock.
there was a small change. Speakers, Ronald Dickman.
Okay. Also, I would like to let you know that it's going to organizing a drive to put the photos, so that if you want to take part in the 90th birthday of Constantino, you have to put your photo right now, okay, in this drive. And Anna will give us more detailed information, the address and so on, so that you can already start applying at all. Okay, but you need to put a photo, okay? Okay, so let's continue this afternoon section. Next speaker is Guilmar Ruiz. Okay, please. Okay.
Listo, ahora vou. Aqui? Tá bom? Okay, I'll try. Well, what I'm going to present today are the essential ideas of a contribution of Professor Giovanni Maddalena, a leading specialist on Charles Sanders Peirce and American pragmatism, and me, to this volume, Vivere la ragione, Living the Reason, with the aim to show you which are the modes of inference and the openings of the logic of surprise that led Constantino to the conception and development of non-extensive statistical mechanics. Coincidentally, the first time I had to talk about Peirce was in a conference of Constantino many years ago in Madrid. And I want to start noting that the word mystery in the scientific divulgation language indicates a rationally solvable problem. And it harbors an ambivalence. There is a secret that struggles to be disclosed. Something is hidden, but incites the desire to know and understand. And from this desire, science is born. This is how Pasteur describes the movement of human energy when it encounters the presence of things. Excuse me. Above this starry vault, what is there? New starry skies. And beyond, the human spirit will never cease to ask itself, pushed by invincible force. What lies beyond? Since the point at which it stops is but a finite magnitude greater than those that have preceded it, as soon as it begins to perceive it, the question always returns, unable to silence the cry of its curiosity. It is useless to answer that beyond there are spaces, times, or magnitudes without limit. The notion of the infinite has this double character of imposing itself and of being incomprehensible. This tension represented by the word mystery is a fascinating question for the philosophy of science, and I dare to say for a true scientist like Constantino. I remember as if it were yesterday when I met Constantino the first time, at a Spanish meeting on statistical physics in 1997. He used a laser point to convince the audience that the human gaze focuses on the anomalous and exceptional events. And humans, we desire to know and understand. And then he helped us to understand with his slides a generalized statistics he conceived to explain an anomalous phenomenon. But how is it possible to attain knowledge about something new? What is the method of knowledge that made possible the genesis of the non-extensive statistical mechanics? To answer this question and illustrate some aspects, we will make use of the epistemological vision of Luigi Giussani, an educator and thinker whose method is based on a critical and systematic awareness of experience in action, in whom I find a profound harmony with Constantino's ontological and epistemological vision. We will also make use of some scientific examples and of the logical work of Peirce, American philosopher, logician, and scientist, who is the father of the modern semiotics. The first step on the road to the knowledge of something new is the recovery of the affective dimension of scientific work. In his premises to achieve accurate knowledge, Giussani insists that knowledge is the fruit of the encounter between human energy and a presence. It is an event in which the energy of human consciousness assimilates the object. Immersing in a mentality that seeks to separate science from affection to be objective, we must recognize that the heart, that is reason and affection, according to the Jewish tradition, is at the center of the cognitive process. Excuse me, can you give me the water? The water, it's there. Thank you. It is an advantage because the capacity of adhesion to reality is what allows us to grasp all the factors. And it is also an advantage because the affective bond will make reasonable the tiring work when the study is hard or the reality is different from what we thought we knew. Amazement is an experience that is full of affective energy, that awakens and maintains intellectual curiosity. As the Greeks, we have a Greek here, recognized when they symbolized wisdom with an owl, with his astonished eyes. Here's how Einstein remembers the first time he experienced it. For how otherwise should it happen that sometimes we wonder quite spontaneously about some experience? A wonder of this kind I experienced as a child of 4 or 5 years when my father showed me a compass. That this needle behaved in such a determinate way did not all fit into the kind of occurrences that could find a place in the unconscious world of concepts. I can still remember that this experience made me a deep and lasting impression upon me. Something deeply hidden had to be behind things. Without for reality, reason is paralyzed. It is necessary to let oneself be struck by reality, not only at the beginning, but at every step. When I ask Constantino why he continues to search a complete explanatory theory, he responded, it is written in a book, it's true. Why does one always want to know more if one knows that no one will ever know everything? I don't know how to answer. It's something mysterious. Love leads to the care of the loved one for a reason that I don't understand, but I recognize that it is so. It is the astonishment in the face of reality that keeps me wondering. One is satisfied if one contributes to know the infinite unknown, and at whatever point you are. Humans are made like that. I can't say why. The second step towards a philosophy or scientific discovery, as Giussani describes it, is that it is necessary to have the presentiment of an accessible order exists, at least in part. A mysterious correspondence with reality in Giussani's terms. He states, for understanding to take place, there must be correspondence. Truth is the correspondence between consciousness and reality. This is the nature of rational dynamism. Correspondence, because reality awakens what characterizes us most, the question, and because the universe allows itself to be known. Here you have some of the witnesses of this experience that Giussani loves to think about. Let us now think about the multitude of scientists and engineers giving their lives and energy to pursue the goal of setting foot on Mars. About Newton, who in formulating the law of gravity dreamed of being able to scrutinize God's designs while feeling like a child. In Darwin, who in elaborating his origin of species, dreamed that the enigma of life would be undecipherable. Linnaeus and Mendeleev, who in classifying plants, animals, and the elements, dreamed that there is a simple order in the universe, which for Pythagoras was related to numbers. The same presentiment led Einstein to affirm that the eternal mystery of the universe is that it is comprehensible. And Gerald Toulouse to add that the most incomprehensible thing about this incomprehensibility is that we seem to be able to understand how we understand. But what does understanding mean? It is not to stop at the cold description of facts. Constantino loves to quote Boltzmann, who said that the fantasy is the cradle of the theory and the experimental observation is its tutor. This is to explain the difference between experimental observations and science, the difference between saying a stone falls, a fact, and saying every stone falls, which places the fact as a modest realization of a general principle. In fact, the realism that affective knowledge promotes tends to be all-encompassing, as Einstein demonstrates when he says of himself, I want to know how God created the world. I'm not interested in this or that phenomenon or in the spectrum of a chemical element. I want to know his thought. The rest is a detail. Let us now see, and this is the third step, how to make this leap without there being anything irrational. Reason tackles this task with a diversity of methods that are constrained to measure themselves against what Giussani calls elementary experience, which is closely related to what Peirce calls in his last period rational instinct. In the conception of modern logic, logic is synonymous with mathematical logics. New ideas, then, would not be the fruit of this restricted logic, since they are not deducible. But Giussani, and for Peirce, logic refers to the theory of reasoning in a broad sense. In addition to the two traditionally recognized modes of inference, deduction and induction, there is a third one, abduction, related to the genesis of scientific theories. Deduction applies an existing scheme to a particular case to reveal consequences. For example, the formula for the perimeter of the circle shows that only 6 meters are needed to raise a rope around the world 1 meter higher. This deduction is necessary, surprising, and more reliable than intuition. In induction, for some case in which something is true, we, infer that it is true for a whole class of phenomena. For example, stones fall to on the earth farther the harder they are from. The moon is a gigantic stone and the earth is round. Then the moon was thrown with so much force that it spins without falling. With such a simple reasoning, Newton unifies the celestial and terrestrial worlds and enunciates the law of the universal gravitation. This generalization helps to know regularities of nature. But these two methods, as we said, are not enough to generate hypotheses to account for facts that surprise us. This there is a third method by which Giussani, together with Peirce, argue that even the irruption of new ideas can be explained in rational terms. Peirce calls it abduction. Abduction describes the process by which we generate hypotheses to account for facts that surprise us. This is how the scientist's mind works when he suspects where the truth lies. First, he observes a surprising fact. C. If X were true, C would be would occur. Then there is a reason to believe that X is true. The example used by Peirce is that of Kepler, who had confronted with the surprising phenomenon of the erroneous position of Mars and deduced that the orbit was elliptical and not circular, as an explanation very different from the previous accepted one. These are the three properties that are necessary to characterize abduction reasoning. It accounts for a surprising phenomenon. Something new has to be discovered, and the solution cannot be a generalization. Abduction, as you know, is an inseparable companion of Constantino. Fourth step, elementary experience and normative value of aesthetics. The fourth step indicates how to deal with the most problematic aspect of abduction, that is, how to formulate an hypothesis. In Peirce's most probable reconstruction, one must perform a rapid reading of the signs. It is not a matter of intuition, but of a very rapid inference, which Giussani recognized in the phenomenon of trust or moral certainty by reproducing the same logic. He says, as a method, the last one is akin to the fear of an artist or a genius who through science proceeds to the perception of what is true. When Newton saw the famous opal fall, it became a sign that immediately sparked his great hypothesis. As you know, for Constantino, a formula in the blackboard related to multifractals became a sign that made him to conceive his skew entropy. Countless scientific discoveries demonstrate that the adaptive leap is based on the aesthetic reading of science. For example, Boltzmann, how was he able to sustain his theory even in the face of violent opposition from the establishment of his time? Because it was very simple. That is, when flipping a coin, the two possible outcomes are equiparable. For such a simple and beautiful statement, he built the theoretical building of statistical mechanics. The importance of beauty is such that it is the basis of a working method. Like this morning, Annie Hansu told us. For me, this fantastic example remains in my memory ligated to Constantino. If I represent the number E, as a sum of infinite terms that follow a rule, I can venture a reasonable hypothesis about the next term is, which is the next term. It is important what we know, but also how it is known, because well represented, as you know, have solved. And when an equation is elegant, besides to reflect the experiments, is ready to be part of something bigger. That's why Dirac considered that it is more important to put beauty into the equations than to fit the exact results. That's why Einstein stated that the experiments that contradicted general relativity were wrong, because the theory was too beautiful. And that is why Poincaré claimed that one studies nature not because it is useful, but because of its beauty. And our friend Constantino seeks the beauty of the equations as a necessary condition for the validity. But what faculty formulates the judgment of greater or lesser aesthetic plausibility in the abduction process? For Peirce, it is the rational instinct, we said, the aspect of our thinking that is in harmony with reality, which explains the incredible human capacity for discovery. For Giussani, it is the elementary experience, the need for totality, which is our reason, or essential capacity for knowledge, or openness to penetrate and embrace reality to an ever greater degree. That is how reason, in the unrestricted sense, faces the task of incorporating new contents through an aesthetic judgment of the data, understood as science. Fifth, and the last step, structural disproportion of the dynamics of reason. I stand that it is a myth to think that we will be able to reach a complete and total knowledge of the laws of nature, as Weinberg intended. We would need to build a particle accelerator of infinite size to know what happened in the first instant of the Big Bang. Larger and larger accelerators are being built, and they bring us closer and closer to the first instant, but we will never reach it. Weinberg also recognized, I must admit that when we'll have a final theory, we will not have a totally satisfactory picture of the world, because there will be always the question, why? Thank goodness, I say, because it should be terrifying to have nothing to wonder about. Moreover, this science does not advance to reach the truth once and for all, but it approaches by successive stages closer and closer affirmation. Peirce called this intrinsic characteristic of science fallibilism, which is the subjective side of the metaphysical realism. If reality is infinite and knowable, all knowledge is always in action. It is always approximate. Peirce states, in fact, the best hypothesis, in the sense of the most recommended itself to the inquirer, is the one which can be the mostly readily refuted as if it is false. If a hypothesis can quickly and easily be cleared away so as to go toward leaving the field free of the main struggle, this is an immense advantage. As when Constantino reformulated the entropy of Volman Gibbs, that 100 years later, after it was conceived, became clear that the old truth was only an approximation, as the non-extensive entropy generalized that all expression and related relationships. If so, where does it lead us to elaborate one theory after another? We go back to Einstein, who describes the affective knowledge, we called it, in a sublime way. Why do we devise theories at all? The answer to the latter question is simply because we enjoy comprehending. There exists a passion for comprehension, just as there exists a passion for music. That passion is rather common in children, but gets lost in most people later on. Without this passion, there would be neither mathematics nor natural science. In conclusion, we have shown a phase of reason and of scientific adventure that is intrinsically open to the novelty that comes from reality. Giussani's epistemology, in consonance with Constantino's, can be a way to conceive science in a non-reductionist way. Giussani called this conception of rationality openness. We see his words. Reason is an infinite embrace of reality. In this conception of reason as openness, as a window open on an infinite field that one never ends up entering, every moment is novelty, a richness. If reason were the measure of things, every moment would be instead a tomb. In the specificity of scientific experience, Giussani introduces the vanishing point in analytical reason. Reason is consciousness of reality according to the totality of its factors. And in the totality of its factors, there is a vanishing point where the accounts do not up. Rational experience, instead of getting stuck, opens up in hunger and thirst of a different horizon. This openness combines respect for the specificity of scientific research within the aspiration to the infinite religiosity and recognition of truth, beauty, and goodness transcendentals. A science thus conceived does not oppose the recognition of the existence of God. Science is a necessary instrument that at his speed it speaks, cannot open the possibility that it reveals.
Thank you, Guilmar. The session is now open for comments or questions or doubts or to dive with you in your thoughts, that you brought us, you shared with us, that I found fantastic. I honestly must confess to you. Okay.
Luciano, you promised you made a question.
Thanks for an inspiring talk. And I'll just add a dissonant note that, of course, there are many beautiful, magnificent theories that died because they don't describe reality.
Because they, excuse me?
They don't describe reality.
They
were killed by experiments.
One might think that the beauty of the theory is necessary, but not sufficient. Not sufficient, yes.
And if I am not wrong, Dirac, in the initial formula was something that it ought to be corrected, but he said it is too beautiful. This must be true. He sustained that theory. He discovered an antiparticle, and later he corrected that term as what not exact. I mean, it is not a contradiction. That approximation, of course, to the experiments, you have to reach it at the end, no? But searching of beauty so many times was a guide to reach that point.
Maybe this is maybe this is an opportunity to say that the way Guiomar described several things there, it fits very well my own feelings when I thought about that entropy. And in particular, one of the thoughts, because of course we never can comprehend the totality of a theory, but there are some points that tell you that this must be true. And one thought that accommodates very well with the kind of things that Guiomar was saying is that I thought in the falls of Iguazu, there is big chaos, the droplets and water going pa, 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 it's crazy. But in the bottom of the Iguazu Falls, the river has vortices that turn around very slowly. And I found always very strange. How come in this chaos of the Iguazu Falls, there can be vortices that turn around slowly, slowly, slowly in the water, and they don't care about the chaos that is originating this. So it came to my mind the thought, what is a vortex? A vortex is a trillion of molecules of water that go like an Indian file, one after the other. Ta, 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 ta. And then I thought, this practically does not exist in this room. The molecules here do not go one after the other like this. So it's a very improbable event. How come can we have all the time they are very stable, a trillion of molecules going around? And the probability is very, very low. How can you make a very low number to become big? You make the square root of it. You take a power of it with a power smaller than 1. And then the small number becomes big. So I said, well, probability to the power Q. And then something which is not important becomes important because you are putting not a weight, a bias on the probability. So it's a very simple thinking, but from very simple thinkings, very usually you arrive to more general concepts. So thank you, Guiomar.
I learned it from you.
Okay, thank you.
Thank you.
So let's thank Guiomar again. Next speaker is Roberto Iglesias. Okay, you're...
El control.
Pointer.
The pointer. Ah, okay.
Okay, good afternoon, everybody. First, I would like to thank Evaldo, Anna, the organizers of this a beautiful meeting. It's for me an honor to be in this meeting that honor our friend Constantino. I did not work with Constantino, but I know him a long time ago, and in some way did parallel paths. First, we both made our graduate studies in the Instituto Balseiro, Centro Atomico Bariloche, and Constantino should remember, oops, this is the infamous Pavilion 4, that was where the students were lodged in the Centro Atomico Bariloche. It was 10 kilometers from Bariloche downtown, but in the winter with the snow, those 10 kilometers may expand up to infinite. So there were a kind of course in this pavilion that was called the White Death. And after the studies of the licenciatura in Física, probably most of you already know that licenciatura in Argentina is not the same that in Brazil. Licenciatura is equivalent to bachelor in physics. And also we both made our PhD thesis in the University Paris Sud in Orsay, France. I think that you finished in 73, 74, and indeed we never met in the same place. I finished in 77, and also in Bariloche we never met. And it was really curious that we met in 1982 in the International Conference of Magnetism, Kyoto, where at that time the organizers provided some help to young participants like us. And part of that help was the lodging. And so we were sharing a room in a hotel in Kyoto. And then we talked, and that way I learned that we had this parallel career. And then it is after that we met many, many times in Brasilia, here in Rio de Janeiro, and in Porto Alegre, where Constantino came many times, sometimes to deliver. I was invited by Rita to deliver lectures on non-extensive terrain. Marcia, okay. Okay, but the subject we are working now with, okay, those are some of the meetings that where we met with Constantino. This was the LAUMP in the Salvador. I don't remember exactly the year. 2003. Roberto, Constantino, and myself. And this was in Colonia in 2002 with my first student in the field, the first postgraduate student in the field of econophysics, Salete Pianegonda, and Constantino was also there. Okay, and now some years after those meetings. We are in this meeting. I am going to talk about taxes, inequality, and equal opportunities. The collaborators in this work are Sebastián González, who is professor in the Instituto de Física in Porto Alegre. Benur Francisco Cardoso was our master student. Then he decided to do a PhD in economics, and he's doing this in Florianopolis. But also he was accepted in an opposition in Petrobras, so he's working in Petrobras at the same time that he's doing his thesis. And more recently, Tiago Diaz, who is a professor in the Technical University of Paraná. So we are going to talk about inequality and reasons and solutions to diminish inequality. Inequality is increasing from the end of the 20th century and at the beginning of the 21st century. There are many reasons. Some authors, this is an example of inequality. This is, for instance, a section of the population of the planet and of the wealth, all the possessions in the planet. So 1% of the population possess 46% of all the wealth in the world. 11% possess 39%, and the rest, 55 plus 33, have only 15% of the wealth. So there is an incredible high inequality in the distribution of wealth, in the distribution of income. This 1% are the millionaires, those that have wealth bigger than $1 million. Okay. Possible reasons. Some authors, like the best known is Thomas Piketty, who wrote a book called The Capital in the 21st Century, is that in the 80s and 90s, Ronald Reagan in the United States and Margaret Thatcher in the United Kingdom succeeded in imposing deregulation in the labor market. So they broke the power of the big unions and started changes in the legislation to abolish or to change some protection of the workers. Also, the fall of the Berlin Wall and the crash of the Soviet Union was also a contribution to increase inequality, because some of the advantage that many countries guarantee to workers were eliminated because there were no more the fear of communism. And more modern now, the end of protection to workers, or the benefits, has been replaced or rebaptized as entrepreneurism. That is, to work by yourself with no any kind of protection. So this is, according to the Swiss banks, this is the total wealth on the world. Wealth, that means properties of some kind of goods, gold, for instance. Okay, this is the total adult population, 5 billion. This is 40 $454 trillion. Those are 5 billion inhabitants. So this lead to $85,000 is the wealth per capita in the world. But it is 85 million, yes. No, it's 85,000. No, this is the decimal point. This is a decimal point, yeah. But in any case, it's a very reasonable amount of money if the distribution was completely equalitarian. Sorry. You want your share? Okay. One of the ways of have a rapid recognition of the increase of the inequality. For many time, one of the representation of inequality was the Lorenz curve. That is essentially to plot the population and the fraction of wealth that each sector of the population possesses. If the distribution is completely uniform, the Lorenz curve will be a straight line. But indeed, most real Lorenz curve have this kind of concave behavior, meaning that the poorer fraction of the population have a very low participation of the wealth, while the higher fraction of the population possess almost half of the total wealth. For instance, in Argentina, the lowest 20% possess 4.8% of the wealth, in Brazil 3.3%. This increase a little for the second 20%, the third, and the highest 20% possess in Argentina 47%, and in Brazil 57%. But this is a rather cumbersome way to measure inequality. So in the year 36, Conrado Gini, that was an Italian economist and mathematician, proposed to measure just the area between the line that would be the hypothetical equalitarian distribution and the Lorenz curve. And the reason of this yellow area over the area of the triangle is what is known as the Gini coefficient or Gini index. As this area is lower than the triangle, the Gini index is a number that is lower than 1, but generally it is multiplied by 100 to have a number that is between 0 and 100. There are two ways to calculate the Gini coefficient. One is to perform the integral in a numerical way, that is to calculate the area under the Lorenz curve and to diminish from the area of the triangle. And the second way, that is the more practical for numerical calculation, the Gini coefficient is just the average value of the difference of all the wealth of every one of the agents in the society, with 1/2 to above counting twice each pair, and divided by the number of agents and by the total wealth. Both formulas deliver the same result, and a Gini coefficient near 1 or near 100 means that this yellow area occupies almost all the triangle, and so it's a case of a strong inequality. That means that almost all Asians have 0 wealth and just a few have all the wealth. And in the other extreme, a Gini coefficient of 0 means perfect equality because the yellow area should be 0 and the Lorentz curve should be this line. Alpha is to normalize in the formula. Yeah. There are many other ways of calculating inequality. There is the tail index, there is the entropy calculated from the distribution of wealth. So, but the Gini coefficient have this advantage of being constrained between 0 and 1 or 0 and 100. Okay, this is from the book of Piketty showing that the Gini coefficient goes through a minimum in the 50s and 60s, that is after the Second War. This is a period of relatively nice wealth distribution, but it is increasing after the 80s and in the 21st century. In the United States, the Gini coefficient in 2021 is 0.44, so more or less here. This is the Gini coefficient in Brazil and Argentina. In Brazil, it decreased during the beginning of the 21st century, and also in Argentina during also the first years of the 21st century. But those data goes up to the end of the Dilma government in Brazil, and here the beginning of the Macri government in Argentina. And now this is the last global value, 2021 in Brazil. It attained the historical record of 67, and in Argentina, 45. 45 is more or less here, and 67 is outside this scale. This scale is very short. It is between 50 and 60. Sorry? No, okay. As I told a minute ago, you can represent the Gini with a number between 0 and 1 or between 0 and 100. In this graph, alô? Agora está bom? Ok. Okay, so I am going 5 minutes. Okay, I am going through the models in a rather fast. The idea is to simulate a society with exchange of money between agents, like the exchange of energy in the kinetic theory of gases. But the difference is that in the kinetic theory of gases, the exchange of energy is completely at random. So a molecule with a very low energy can acquire a very high energy in a collision. In the models for economic agent, we represent each agent with a given wealth and also with a given risk aversion, that is, when he interacts with other agents, he tries to save a fraction of the wealth. And the exchange is in a way that no one can win more than the other. So this is called the minimum rule. The exchanged quantity is the minimum of the quantity that each one put at stake in the interaction. And also, this is an hypothesis to simplify the calculation. The total wealth is conserved. The interesting point with this rule, that this is a fair rule, that is, no one can win more than he has, is that this leads to the opposite of the equipartition of energy of the kinetic theory of gases. This leads indeed to condensation. All the wealth concentrates in one or a very small group, but of agents, or to one agent. This is called condensation, and with Ben-Hur, we have demonstrated this in a theorem, that equal opportunities in this kind of exchange model always leads to condensation. That is, the derivative in time of the Gini coefficient is always greater or equal to 0. This is like the second law of thermodynamics for the entropy, but in the opposite way, because the maximum of the entropy is when you attain the equipartition of energy. Here, you attain the maximum of the Gini coefficient when all the wealth is concentrated in just one agent. I will not enter in the detail of the calculation of the theorem. One of the negative points of condensation, that if almost all agents have zero wealth, they cannot participate in the economy, they cannot participate in the trade, so the economy dies when there is total condensation of the wealth. One author, Bruce Bogosian, published an article, very didactical, in Scientific American in 19, and showing why this happened. He said, you have 101 casinos proposed to pay 20% of your bet if you win, or to take 17% if you lose. The casino is fair, so the chances of winning or losing are 50%. That is not the situation in real casinos. And the expected value is bigger than 100. There is, in principle, a profit of 1.5. But the secret of this casino is that in the zone Hotel California, you can check in anytime you like, but you can never leave. So you must keep your money in this process. And Bogosian shows that if you play 10 times and win 5 and lose 5, the final capital is 1.2 to the 5, 0.83 to the 5 times 100 is 9802. So you are losing money even if you won half of the time. And if you play 1,000 times, your capital is reduced to 13.48. So this phenomena in an infinite series of time leads to condensation. So how to avoid condensation? Okay, one first idea in the beginning of the century was to increase the probability that the poorer agent win more in the exchange. So this factor is a factor that increases the probability of winning of the poorer agent. This is rather artificial. There is no way to verify this in an exchange. And also it seems to be the opposite of real situation where the richer agents have a bigger probability of winning. So the real solution are taxes. We have two kinds of taxes: taxes on the wealth or on the fortune, and taxes on the exchanges. For instance, in the trade, when you buy an object, you pay a certain fraction of the value of this object as taxes. So we have simulated in a series of articles the taxes, and there are two parameters to consider. First is what is the percentage of money to be deduced as taxes, and then how this money is redistributed among the population. You can think of a universal assignation, with everybody receives a fraction of the money taken as taxes, or you can prioritize the poorer agents. So here is the blue line is universal distribution. Everybody receives a fraction. This is the Gini coefficient as a function of the percentage of taxes. The real percentage should be in this region. There are no taxes bigger than 25%. And you can see that when you choose just the poorer fraction of the population, the Gini coefficients attains a minimum lower than if you made a universal redistribution. This is for taxes on the fortune. For taxes on exchanges, I will just, this is the paper, the article is here if you want to. Taxes on exchanges produce also a reduce of the Gini coefficient, but is lower than the tax on the fortune. And we can combine both taxes. I will not enter into the details. Here is the value of the taxes and the Gini. If the taxes are on the wealth or on the fortune, the Gini coefficient decrease very much than for the case of taxes on the trade. This is when the redistribution is directed to a fraction of the population. Here is universal redistribution. And this is just what is the fraction of the population that receive the benefit. And here the Gini coefficient for different values of the taxes. So you see that in general, taxes on the fortune are more effective to reduce inequality, with the exception of this value. This value is not realistic. It's an enormous taxes, bigger than in Sweden. Okay, so the conclusions is that on one side, the very high inequality is an obstacle to trade and to economic growth. In the extreme case of condensation, the trade goes to zero, but this is the tendency that we observed the last years. And we did another article that I didn't mention here, where the agents can learn how to behave to trying to increase their gains, and this increase inequality. And finally, that tax on fortune is more effective to reduce inequality than tax on income. And I'm sorry for being a little late, and I finish here. Feliz cumpleaños.
Thank you, Roberto, for the presentation. It's time for one question. Eugenio?
Well, your conclusion is clear from the graphics you showed. However, in the dynamics, if you impose this patrimonial tax, it's like once or what? Because you have a certain fortune, and then you pay taxes a few times, and your fortune is gone.
No, okay. Patrimonial taxes can happen, for instance, the proposal is Piketty is taxing the inheritance. That is a way of taxing, and also a periodic tax on the biggest fortunes that is, for instance, collected every year, or when there is a change in the fortune, so you tax the difference in between the previous one, between the new value and the previous one. Okay, but some kind of tax on fortunes, for instance, tax of fortune and taxes also over capital gains or financial gains. That is very, very difficult to put in practice, because there are always those fiscal paradise where there are no taxes. But that could be a way of getting more money for the distribution. For instance, in Brazil, if you have money in the bank, but you have an amount of the order of $50,000, you pay enormous taxes. But if you have more than $1 million or $2 million, and particularly if the money is not in Brazil, is in the Bahamas, you pay no tax. So the government is trying to arrive to an agreement with the Chamber of Deputies and the senators to put some kind of taxes on big fortunes, and also on the inheritance.
Okay. Thank you, Roberto. A quick, okay. I get some, like, we have the last speaker present. It's Ignacio. Okay, Ignacio.
Well, first of all, I would like to thank the organizers, Evaldo, Fernando, and Hans, to give me the opportunity to be here. It's always a pleasure. In this special occasion, the 80th birthday of Constantino. which represents a great inspiration for me, and this works reflects this influence. I'm going to talk about a generalization of the random walk using the underlying mathematical structure of non-statistic statistics, Tsallis statistics. And here we have the content of the talk. First, I give a brief preliminaries about random walk. And then we go to the formulation of the random walk, a generalization of random walk using the Q algebra that belongs to the is the underlying mathematical structure of the Tsallis statistics. And finally, some conclusions perspectives are outlined. Well, this doesn't don't mean this means a brief historical review. In the words of Tito Lucrecio Caro, that represents a chronological, at least I think it is a chronological description of the ancestors of the random walk. In this, citing these sentences, the atoms moves in an infinite vacuum. The universe is composed by atoms and vacuum, nothing else, because we are made up of a soup of atoms in constant motion. Life forms in this world and in others are in constant movement, increasing the power of some forms and decreasing that of others. Feelings perceive the macroscopic collisions and interactions of bodies. So these sentences in some way represent an early attempt of describing the random movements of the molecules colliding each with other. But it was not until the 19th century that biologist Robert Brown observed that particles found in grains of pollen in water moved through the water with movements of their own volition. And then in 1905, Albert Einstein proposed the first theory of Brownian motion, obtaining this expression for the diffusion coefficient. And then we can mention also the French physicist Paul Langevin that establishes the well-known Langevin equation, which describes the movement of the particle colliding with molecules of a fluid. Experimenting this interaction can be modeled by a random force. Well, here's it's a simple illustration of the grain of pollen colliding with atomic particles, and the results, the net movement of this results random. And here simply we are recalling that we can pass from the microscopic description to the probabilistic description in terms of some master equation that it represents one of the main tools of in order to obtain the relationship between the random walk and the resultant Fokker-Planck equation. Well, and here we have the definition of the classical random walk. Here we are treating the classical case, and the conditions are given by these probabilities. The sum equals to 1, and the mean value of the variance represent depends on the value of P. We are considering the symmetric case for the sake of simplicity. So we are going to generalize the random walk considering this symmetric condition. Another feature important of the random walk is the Pascal triangle. Here we have, after 5 steps, we can see that the probability is concentrated around x equal to 0, because we begin at x equal to 0, and this we'll see that will not the case for the deformed random walk. That is by introducing a deformation on the random walk. Well, we can see also the trajectories, which reflects homogeneity in the sense that there is no position privileged. So we can consider that the space is homogeneous in this sense. And here's simply code for making, constructing this trajectory. And simply we have to sum the values of each step. Well, an important feature is the connection between the random walk and the diffusion equation. And this can be accomplished by means of this convex combination of probabilities at time t in order to obtain the probability at time t plus delta t, and taking the limits of the lattice parameter and time interval going to 0, and using these approximations, maintaining the terms up order 2, we can obtain the well-known Fokker-Planck equation for the free case, remaining this coefficient finite. Well, here we have typical evolution of the free solution case. They are Gaussian functions, and this is not the case when we introduce a deformation, because we will see that there exists a preferred position for the deformed random walk. Well, we begin, now we go to the deformed random walk, mentioning the principal motivations. Of course, the seminal work of a possible generalization of Boltzmann-Gibbs statistics of Constantino represents the moment where the Tsallis entropy was revealed to the world, and from this time up now, we can mention an interesting property that is the non-additivity, which appears here in this equation, that where we can extract a particular Q-sum, and from this Q-sum we can construct a Q-algebra. By employing the corresponding K-exponential, we can complete this Q-algebra by means of key product, and the rest of operations are simply the opposite of these ones. From the subtraction, the form subtraction, we can also define Q derivatives, and this is a crucial point, because the form of Planck equation depends on these Q derivatives. We can also mention that this formulation of the generalization of the Q algebra was made at the same time by Ernesto and Ivanen. And one of the applications, maybe an interesting application, is the possibility to make a mapping between harmonics oscillator with deformed derivative and another type of potentials. And this was made in this paper of Raimundo Costafilho. This constitutes an interesting research line, because basically one can generate a family of potentials by means the potential of the harmonic oscillator by deforming the kinetic operator. And we can only use a canonical transformation. And this we can mention as the second motivation. And then together with Ernesto and Bruno, we study a generalization of the Langevin equation by introducing a position-dependent mass. And we arrived to a deformed Fokker-Planck equation that is simply the Fokker-Planck equation with the derivatives replaced by the deformed derivatives. And an important result was the existence of a one-to-one correspondence between position-dependent mass and the deformed derivative. And at least this was verified in the context of diffusion equations and Schrödinger equation, it may be constitutes a conjecture that this can be extended in other contexts. Well, with this in mind, the next step was to study a deformation applied to the random walk. Here we don't have a position-dependent mass, but we can employ the Q sum of the Q algebra, and in this way we obtain this recent article where the main characteristics are the suppression of randomness and inhomogeneous diffusion. Well, the strategy is very simple. We can define a random walk in the formed space that is in the space given by the canonical transformation corresponding to the Q deformation, and with the same conditions, we now have the form steps. So the range of values of the random walk now are numbers that are not non-integers. It depends strongly of the deformation parameter. But here a question arises. With this structure of the random walk in the deformed space, what is the corresponding random walk in the standard space? And to accomplish, to answer these questions, we used this nice property that says the Q sum, which simply means that on one way we can make this sum of deformed numbers, or equivalent we can apply first the Q sum and deform the result. In this way we can express in a standard pace the result of this deformed trajectory. And now we can see that there exists as a power series of perturbative corrections and the deformation parameter in the deformed case. Well, and here we have another novelty from this construction, a comparison between the Pascal's triangle and the deformed Pascal triangle is that here the positions are not integers, can be rational, typically rational numbers. And we can see that the probability now is concentrated around a value that is exactly the minus gamma, the inverse of minus the inverse of gamma, the formation parameter. And here we see a plot of the trajectories for two values of gamma equals to 1/2 and minus 1/2. And we can see that there exists a transient that quickly disappears after more or less 1,000 steps. This is a characteristic that this deformed random walk, this type of random walk eliminates the randomness in a few number of steps. At least this was verified numerically, and also we have a convergence theorems that simply state that the limit, asymptotic limit of random walk is given by the deformation parameter, and the behavior is exponential. Still, we can prove this behavior, but numerically we can we have verified this. In this plot, we can see the exponential fitting the deformed random walk. Well, and now the connection between the deformed random walk and this associated diffusion equation, it can be accomplished in the same way as in the standard random walk. It's the same type of count in the deformed space, the same convex combination, and taking the limits, identical limits as in the standard case, using this property of the deformation for any number near to 0, the deformation doesn't affect the number. We arrive to a deformed diffusion equation, the deformed Fokker-Planck equation obtained in the paper with Ernesto and Bruno. So this shows some consistency between the deformed random walk originated by the QS algebra and the deformed Fokker-Planck equation originated by the position-dependent mass, the Q position-dependent mass associated to the Q algebra. Well, and what is the relation between the distribution in standard space and in the deformed space is given by this formula that indicates a divergence of the probability distribution given by the deformation parameter. And another feature is that the deformed Fokker-Planck equation corresponds to a particular case of the Van Kampen diffusion, where the diffusion coefficient is given by this, by the deformation parameter. Hence, we can obtain the inhomogeneous free diffusion solution by means the homogeneous free diffusion, simply writing this expression in terms of by means of the canonical transformation. So the solution for the free case of the inhomogeneous diffusion of the deformed Fokker-Planck equation is given by this formula. Here we have some plots of these solutions. We can see that the localization is fast around the divergence of the distribution. So we begin with the delta function and we end in the delta displaced from the origin in this value. And another novelty is now we have a characteristic time that depends on the deformation parameter. Well, in order to study the type of diffusion, we plot the mean standard deviation. Here the curve in black represents the standard case. And this means that in the limit of gamma q going to 0, we recover the linear diffusion. It's an hyper-exponential behavior given by this exponential. This means the following. We are using linear derivatives, so we can expect non-linear behavior. So this type of deformation only gives inhomogeneous diffusion. So if we want to get a nonlinear effect, we must use nonlinear derivative, but it's more complicated and is clearly can constitute future researches. It is instructed to make a comparison of the principal features between the random walk and the deformed random walk. The Pascal triangle lost his symmetry in the deformed random walk. We have randomness in the standard case, and this characteristic is eliminated in the deformed random walk after 1,000 steps. We have an asymptotic limit in the deformed random walk, and the Q sum is present to calculate the trajectory of the deformed random walk. We have, in both cases, we don't have memory effects. The diffusion equation maintains the form, but written in the deformed space. We have different stationary solutions, and the the mean standard deviation is linear in the standard case and exponential in the deformed case. Characteristic time is infinite in the standard case and now depends in the deformed case on the deformation parameter. And we have a localization in the deformed random walk that depends or is controlled by the deformation parameter. Well, now we give some conclusions. Some of the main conclusions: a suppression of randomness is observed for the deformed random walk for gamma q between -1 and 1, reflected in the conversion of any trajectory starting at x equals to 0, with the asymptotic limit being given by this value minus the inverse of the gamma q. Exponential conversion of the deformed random walk trajectories is a consequence of the q deformation used, because we also can use other type of deformation. For instance, the Kanyadakis associated to kappa statistic, etc. The master equation of the deformed random walk implies a deformed Fokker-Planck equation that results a particular case of the inhomogeneous Van Kampen diffusion. We have a localization at finite characteristic times that are signatures of this deformed random walk. And other deformation could be used to generate other deformed random walks, for instance, using the kinetic statistics. Here, simply we have an extension to the two-dimensional case. The principal problem is the one-dimensional, because the two-dimensional are independent directions. And here we have some plots, so some reference. And happy birthday, Constantino. Thank you for attention.
Thank you, Ignacio. Session's open. Okay.
It is just to say that there is a couple of typos in your presentation. When you show the Pascal triangle, the number on top is a 1, not a 0. The 0 there and the 1 on top, it should be a 1. This is a 1, number 1, and the other one on top also. The one below. No, this one is the number.
This.
The first number in the Pascal triangle is a 1, not a 0.
I don't know if it's maybe 1.
1. Mm-hmm.
So I must correct this,
okay.
This one.
Another questions? I could not understand something. What you said is this exponential divergence, but the x converges to a fixed point. I really do not.
Yes.
That sounds contradictory to me.
Well, numerically we can see that this is the.
Okay.
Because these are exponentials. Yes.
Okay.
And asymptotic behavior is given, can be approximated by.
Okay, but then you, in the table that you showed on the end.
Then.
And that was also what Constantino asked. What is, why it grows exponentially if what is growing exponentially? I really could not understand this.
This expression grows exponentially for t going to infinite. I interpret this as exponential.
But if it's localized, what's converging is how the mean square deviation can.
Here we have the mean standard deviation. For instance, for a deformation, a grade deformation equals to 0.8. At the same.
What? The mean is okay. Okay, the mean is stuck. Okay, the mean is stuck. Okay, is that what you understand? Because you say that x is.
Well, here we have with the description in terms of the probability distribution and the random walks. has a behavior strictly exponential.
Okay. Something has skipped mid, then I could not follow properly. Okay. Any further questions? So let's thank Ignacio again.
Thank you very much.
The session's closed. Tomorrow we meet again at 9:30. Okay. Do you have an announcement? Okay.